Very good morning. We'll start the inaugural program in another 5 minutes. The chief guest has arrived. Meanwhile, I request all the delegates who are sitting in the back rows, please occupy the vacant seats in the front rows. I welcome Professor Arindam Ghosh, sir. Welcome, sir. Yes. So, ellarigu shubhodaya. Very good morning to one and all. Also, on behalf of Karnataka Science and Technology Academy, Department of Science and Technology, Government of Karnataka, we are organizing this 3 days special lecture series on quantum technologies, fundamentals, computation and applications. So before starting this inauguration program, I request our dignitaries to come on the dais. Professor A.H. Rajasab sir, Chairman KSTA, Professor Arindam Ghosh sir, Dr. Anandar and Shri V.K. Srinivas. Now I request everyone to stand for our state anthem, Nadagite. Thank you. Now we will be playing our KSTA Vijnana Geete. You can sit, please. Please be seated. Thank you. Now I request our CEO Dr. Anandar sir to welcome and give the overview of the program.
ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. A very good morning to all. Today we are here for inauguration of 3-day workshop on quantum technologies, fundamentals, computation and applications. Honorable Minister for Mine Irrigation, Science and Technology, Shri N.S. Bosaraju sir was expected to grace this occasion. However, as he was engaged in an important government program at Traichur yesterday, he could not be physically present for today's event. He has conveyed his best wishes for the program, and we sincerely thank Honorable Minister for his continued support and encouragement. We are pleased to note that he may join us online. We extend a warm welcome to the Honorable Minister, his personal secretaries and other officials from this office. Today's inaugural function is presided over by our beloved Honorable Chairman, Professor Rajasab A.H. Professor Rajasab A.H. is a distinguished academician with 43 years of teaching and research experience and more than 30 years in higher education administration. Known for his integrity and visionary leadership, he has played a pivotal role in institutional development, policy reforms, and international collaborations. He has held several prestigious positions, including Vice Chancellor of Tumkur University, Dean of Science and Technology, Registrar Evaluation, Gulbarga University, as well as President of Rai Technology University, Bengaluru. Internationally, he has served as a visiting professor at University of California, Davis, Tianjin, and Bei Agriculture University in China, and worked in senior academic roles in Saudi Arabia, Ethiopia, Eritrea. His areas of expertise include university governance, academic auditing, financial management, examination reforms. A dedicated researcher and mentor, Professor Raja Saab has supervised 20 PhD and 20 MPhil scholars, guided over 100 master students, and evaluated more than 50 doctoral theses. He has published 91 research papers, authored 6 books, and written more than 20 popular science articles in Kannada. His global academic contribution includes 16 international and 264 national conferences where he delivered lectures, presented research, and chaired sessions. He has received numerous honors including Paryavana Mitra Award, K.C. Mehta and Manorama Mitra Award, Young Scientist Award, and Higher Education Leadership Award. A fellow of KSTA, IPS, IS, MPP, and IAS, he has actively contributed to the national committees such as NAC, RUSA, and NEP 2020. Sir, he continues to be an influential force in shaping higher education and advancing research. With this brief background, I welcome our chairman on behalf of all the participants and on my personal behalf. We have with us Professor Arindam Ghosh as our chief guest. He will be delivering a talk after this inaugural function. I'll give a brief overview of his achievements. Professor Arindam Ghosh is a professor in Department of Physics at Indian Institute of Science, Bengaluru. He obtained his BSc from Calcutta University and completed his MS and PhD from Indian Institute of Science. His research focuses on experimental condensed matter physics, particularly electronic transport, noise phenomena, and optoelectronic in atomically thin and two-dimensional materials such as graphene and van der Waals heterostructures. Professor Ghosh has held a postdoctoral position at University of Cambridge and visiting fellowship at IBM USA. He is a recipient of several prestigious awards, including Shanti Swarup Bhatnagar Prize and Swarna Jayanti Fellowship. I welcome Professor Arindam Ghosh on behalf of KSTA and on behalf of all of you. We have many dignitaries among the August gathering. I welcome Professor Prasad Hamsawant, Principal, Cambridge Institute of Technology, to this inaugural function. I also welcome Mr. Darshan Kumar, Research Scholars, MIT USA, and Startup and Entrepreneur, AION, has graced this occasion. I welcome Mr. Darshan on behalf of KSTA and on behalf of all the participants. I welcome all the resource experts and all the dignitaries who are present in this function. I also welcome Sri V.K. Srinivasu, who is coordinating this program. I welcome all my colleagues and all those who are directly or indirectly involved in this program. I welcome media team members who are covering this program. I welcome all the participants to this inaugural function. I welcome those witness this program through social media platform for this inaugural function. Welcome one and all.
Thank you very much, sir, and on behalf of all of us, we also welcome you. Now I request dignitaries on the dais to formally inaugurate the program by watering the plant. you very much, sir. Now I would like to request our chief guest, Professor Arindam Ghosh, sir, to address the gathering.
Thank you very much, and for inviting me. It is a pleasure to come here. This is my first involvement in an event organized by KSTA, and I've been learning and all the very interesting programs. What I really like is the forward-looking approach that Karnataka state, is taking for cutting-edge technologies, and I think this is going to be one of the most important pathway forward into making a very strong social impact. Today, AI and quantum are the two most important areas of societal as well as academic developments when it comes to technologies. And the way I have seen the state has taken initiative, I always give examples of this. This is a model that all states in India must take. Okay. This is an example of how through efficient offices, establishments, that you not only go to the highest technological advances, cutting edge technology, but also make an ecosystem of that technology within the local state and communities. It is only through the local ecosystem, it's only through people who are around us where we can make a serious impact. And KSTA's role in this is going to be absolutely crucial. Okay? Reaching out to the people, reaching out, because I move around a lot of places in Karnataka, in different parts of Karnataka, by Mysore, Raichur, various other places, and I find the amount of talent, the amount of enthusiasm, the amount of knowledge that's there is enormous resource that as a state and as a country, we should be in a position to engage and make a collective effort. See, there is a difference between simply knowing something and then having people to, and reproducing it, doing good in exam and so on and so forth. But most important thing is that when we know each other, when we know that this opportunity exists, when we know that this is the way we can contribute along with others, that's when the real development happens. It's a collective effort. It is never an individualistic effort. And this is where the efforts that we are here today on a cutting edge technology, where people have come from different parts of the community, this is where we must start talking to each other. This is where we must understand what the other person is doing. We are, I'm going to show you in my talk how we are trying to enable this ecosystem, how with the collaboration with KSTA and other offices of Karnataka state, we can reach out to different parts of the state, not just around Bangalore. Extremely important to understand, Bangalore is one of the developed places, but we have Dharwad, we have Raichur, we have Mysore, we have many other spaces where there is so much of people that how do we get them all on board, something that we need to start thinking about. And whether local language, quantum in Kannada is one of the fantastic programs that I heard, and it must be taken up very seriously. Okay. And our offices, I head the ISC Quantum Technology Initiative. Of course, my office will always be ready to help KSTA in achieving its purpose, in achieving its goal, in whatever initiative from our side, the infrastructure, both teaching infrastructure, we will be ready to help all the time. I would like to finish this saying that this is one of the most important technological areas, quantum technology. AI and quantum are the two most important technological areas these days. And we must teach ourselves the nuances and the possibilities, particularly economic possibilities, so that we can make a real difference at the societal level. So I hope that this event will give you that entry point about where the money and where that knowledge lies, And we will all be in a position at the end to have a little bit of idea about where we can contribute. I wish you all the best, and I wish the program a success. Thank you.
Thank you very much, sir, for enlightening us with highlights of Karnataka government initiatives along with Indian Institute of Science Research Centers and other educational institutes in quantum technologies. Now I request our chairman, sir, Professor H. Raja sir, to give presidential address.
ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರಗಳು. In this beautiful morning, we are delighted to see all of you and each one of you. There are students as well as research scholars as well as faculty members who are attending this very important, scientifically important conference. So there are about 100 delegates, sir. And these delegates have come from different institutes, well-reputed institutes like Cambridge University, Seshadripuram College, Reva University, Presidency University, Tumkur University, JSS Science and Technology University, New Horizon College, Acharya Institute, BMS College of Engineering, STC Engineering College, then Engineering First Grade College, Patna University, and then Andhra University. And amongst them, there may be some more also whom I have not listed. There are some from North Karnataka also. Some have already come, some are maybe on the way. So there are more than 100 participants from different parts of Karnataka. So it is more a heterogeneous group, and we are happy we are reaching to all colleges and universities in Karnataka, and they are responding well. And this conference especially is of great importance for us because it is a very emerging field, quantum technology, and I really compliment and congratulate, congratulate our staff, our CEO, Dr. Anand, and Dr. Srinivas, and Dr. Umesh, and our administrator, Madheva Gowda, and all others who are working for this since more than 2 months. Now it has come to reality. We welcome all of you very wholeheartedly. Please attend to this conference, and we will take care of you. We keep you comfortable, and you try to interact with one another. And also we have invited about 11 very well-known scientists and professors from different parts of Karnataka, India, as well as mostly from Bengaluru. They are giving lectures, presentations on quantum technology. And when we discussed who has to be invited for this conference as a chief guest, and we overwhelmingly happy, unanimously said Arvind Ghosh is the right person, because we have seen him in different conferences. The 2 conferences on quantum technology, which were arranged in Nehru Planetarium. Professor was there from Indian Institute of Science. One was preparatory conference, one was final conference, arranged by Department of Science and Technology under the leadership of our Honorable Minister Bosraju. They helped the ministry to organize that conference, and they brought in 2 Nobel laureates. 2 Nobel laureates came and they gave lectures. This is about 3-4 months before, soon after the quantum news which came from Amravati, Andhra Pradesh. So the dynamic Chief Minister of Amravati organized quantum activities in Amravati, and he devoted, earmarked 600 crore for quantum technology research and extension. Soon after, we also, Bangaloreans in no way less, our ministry organized a mega conference, because you will not get any better facility in any other city other than Bangalore. So naturally Bangalore attracts the intellectuals as well as the scientists, and our ministry has done its best to earmark the land of 125 acres near IIHR. It is under the process, and the Karnataka government has earmarked 1,000 crores for quantum technology. I am basically a professor of life sciences, especially in nanobiotechnology, and I heard very less of quantum technology till I attended those two conferences. It really excited me. I knew only quantum mechanics is studied since so many years. It is one of the papers in physics master courses in our university. It is not a new science, but now quantum is the buzzword. Quantum is going to be useful in biodiversity conservation, ecological conservation, then medical diagnostic and quantum communication, quantum engineering, quantum laboratories, whatnot. I'm not sure whether AI will be replaced by quantum, but I am sure that AI and quantum will be supplemented with one another. We will have a still mega situation where the last man will be helped. Last man means the village, the person who are in the villages should be helped by this emerging technologies. And in Ramaya, we had a workshop in Ramaya Institute of Technology. We had workshop on quantum technology, and one professor, Reggie Philip, came from Raman Research Institute. He gave a wonderful lecture. Then it opened my insights again. Such a upcoming emerging field of science is quantum technology. So when Dr. Anand asked me, you should preside over, I am from biological sciences, then I was thinking what I have to talk as a chairman of this function, president of this function. I went through, as you all do, that chat GPT, which is not a good thing. I am sure that chat GPT will not encourage our original thinking. I am 100% sure. I am a teacher. But ChatGPT helps us to assess a subject, overall knowledge what is there in the subject. Just a bird eye view we get with ChatGPT. But if you want to go good research, you have to use your own brain. Creative thinking, original thinking, and hard work and coordination, contacting the scientists. Then only we can do good research. But I entered into normal activity as our students do. I went through. So quantum technology is applicable. I will not read this, don't be afraid of me. Quantum communication, then quantum computing, then quantum machine learning, quantum sensors, and quantum in education also in coming days. These are the main fields, including agriculture. In agriculture. And also it is possible to find out what is there underground, below the earth also. So I cannot imagine where all and whom all this quantum technology is going to reach in next 5 years. But if it reaches in a very beneficial way, like AI, we also have quantum, both good and bad, but we have to use it for our welfare and good. If scientists do good initiative, definitely even our rural mass, it can reach our rural mass, and we can expect some good things from the quantum also. Then to my surprise, one company from Bangalore, QPI, okay, they were to be present here today, but they are in a meeting elsewhere. But it is okay. For the valedictory function, one of their functionaries is coming. QPIA invited KSTA to visit their what is that? Can I say industry or office? Lab in that Manyata Tech Park. It is in we went there, and it was a great eye opener for me. They showed me quantum machine and all that, and how the chips can be assessed there, and especially in space technology, quantum this science can be very useful. All that they explained me, and I invited them for this conference. And it is kind of them that they have also permitted Dr. Srinivas to take all of you for a visit on third day, on second day, that is tomorrow. Tomorrow afternoon there is visit to quantum that office. So don't miss. don't miss and please go and visit, and it is going to be a wonderful experience. And for he said qubits, and the machine which they have developed is about 25 qubits, if I am right, and they are ready to develop the laboratories in colleges for with a machine of 10 qubits, they said, and the cost of that machine is 11 crores. Including maintenance, it comes to 13 crores. This is the value of that machine, and imagine what all it can do for welfare of the human beings and also in the education system. I am not sure whether Indian Institute of Science has started bachelor degree in quantum science or master degree in quantum science in India, whether other institutes have started or not. If not, definitely such of the courses will come in coming days. This is what is my assessment. So in India, this QPI AI, then QNU labs, and like that there are at least about half a dozen companies which are working on this. So India really is doing well in this. They have got the correct picture of the quantum technology. Things are coming up very nicely. And I am particularly very much happy and thankful to Arindam Ghosh because he devoted some time in his busy schedule. He gave us some time to come here and address you, and also he is going to deliver a keynote address. When we just had a tea in my office, we were discussing about Quantum Kannada, because English is fine, but it should also go to our villagers. I mean, ರೈತರಿಗೆ ಹೋಗಬೇಕು, ರೈತರಿಗೆ ಬೆನಿಫಿಟ್ ಆಗಬೇಕು, ಅಟ್ಲೀಸ್ಟ್ ಇದು ಏನು ಸೈನ್ಸ್ ಅನ್ನೋದು ರೈತರಿಗೆ ಗೊತ್ತಾಗಬೇಕು. So he was very encouraging, and he said he is ready to collaborate with KSTA with regard to Quantum Kannada initiatives, and also there is one science gallery in Veterinary College, Hebbal. They also have some good resource persons in presence of you all and our officers. I have no hesitation in saying that Quantum Kannada encouragement is needed, and we will do our best to bring all the excellent brains together who are capable of writing in Kannada. We will publish something in that field also. With these remarks, I stop here. I again thank all of you, and all the good arrangements I am sure Kstacademy has made. Make use of our facilities. Those who are staying here in our guest house, you are welcome also. Food arrangements are done. Our food is very, normal food, healthy food, I can say. No any modern pizza, no. Good food we are giving. And our campus is very beautiful. Small campus, but very beautiful. Enjoy the stay. Be happy, make friends. Thank you very much.
Thank you very much, sir, for highlighting quantum technology for social development and welfare. Now, I would like to welcome our Senior Scientific Officer, Shri Vikesh Srinivasu, to give vote of thanks.
Thank you, Umesh. Very good morning to one and all. Distinguished dignitaries on the dais, dignitaries of the dais, dear delegates of the program, friends, ladies and gentlemen. I deem it a privilege to propose a vote of thanks on this occasion. On behalf of all of us present here, I would like to thank enormously our source of inspiration and encouragement, our beloved Chairman of KSTA, Professor H. Rajasab sir, for the valuable support and guidance to organize this event. Thank you very much, sir. On behalf of the KSTA and all of you, and on my thank you very much, sir. On behalf of KSTA and all of you, on my own behalf, I wish to thank immensely Professor Arindam Ghosh sir, convener Quantum Technology Initiative, and also Professor of Physics at IISc, for accepting our invitation as a chief guest to grace this occasion and also to deliver the distinguished talk. Thank you very much, sir, for your kind support. On behalf of all of us present here, I would like to thank enormously our source of inspiration and encouragement, our beloved CEO of KSTA, Dr. Anand sir, for his continuous support and cooperation to organize this training program. On behalf of KST and all of you, on my own behalf, I wish to thank immensely Sri Darshan Kumar, research scholar at MIT USA, for his kind support and for finding out resource experts for this training program. Thank you very much, Darshan, for your kind support. And heartfelt thanks to all the resource experts for accepting our invitation. First of all, Dr. C.M. Chandrasekhar sir from AASC, Dr. M. Sai Baba from NIAS, and Sri Darshan Kumar, and Dr. Ranjani Priyadarshini Madam, and Dr. Amit Kumar Chauhan, and Mr. Sagar Dolin, and Sri Jay Shah, and Davala Suri, and Dr. Sayan Srinivas Garani sir from IASC, and Dr. Elamugat from CENS. So all the resource persons, they kindly accepted our invitation to grace to give the lecture in this 3 days workshop. I also extend heartfelt thanks to Professor Amsavat Nayak sir from Cambridge Institute of Technology for deputing 11 faculty members from his institute, and I also thanks to Professor Santanu Das from Seshadripuram College, and Professor Basvaraju from IISc, and also extend heartfelt thanks to all of you, teaching faculty, research scholars, and PG students of various colleges and universities for attending in this training program. We are very much thankful to all the concerned authorities of the respected universities, colleges for deputing all of you for this training program. Our chairman sir forget to tell, even Madurai Kamarajan University 7 or 8 faculty members also came from Madurai. I also extend my hearty thanks to my colleagues, Sri Madhayagoda sir, admin officer, Sri Umesh Gadki, scientific officer, Mr. Santraj and Dilip Kumar from account section, Mr. Chandrasekhar Murthy and Umesh Keshi, Mr. Panduranga, Ms. Leelu, Mr. Bharat Kumar Mohan, and other KST staff for their kind help and support to organize this event. We extend our sincere gratitude to Dr. Anthony Lobo and his team from Manipal Institute of Higher Education for video and photography of this event. Once again, a heartfelt thanks to all of you gathering here. Thank you, Anandal.
Thank you very much, sir. On behalf of all of us present here, we would like to thank you. Now we will be having a keynote address by Professor Arindam Ghosh, sir. After that, we will be having a tea break.
I would like to just introduce already our CEO sir introduced about
That other computer.
Professor Arindam Ghosh sir. So brief introduction about Arindam Ghosh sir, convener of Quantum Technology Initiative and professor in the Department of Physics, IISc.
No.
Sir, research group is involved in investigating structural, electrical and magnetic properties of various nanoscale systems. Sir, research interests extend from fundamental quantum mechanical effects on charge and spin states in nanosystems to carbon-based electronics, critical behavior in smart materials to new schemes of sensing with nano, micro, electrochemical sensors. With this brief introduction about sir, once again on behalf of all of you, heartily welcome you, sir, for delivering this talk.
Thank you. Thank you, Srinivasji. I think before I start, I just want to, it's working. Good. See, before I start, I just want to say that, IISc Bangalore started MTech program in quantum technologies. Now it is about 5 years old. First time in India. And after that, for the next year, we started the quantum BTech minor in quantum technologies. And in 2024, I chaired a committee from the National Quantum Mission to start the BTech minor in quantum technologies for all the AICTE approved colleges across India. It's about 9,000 colleges. And then after that, that is 2025 end, just about about a month, a little bit more than a month ago, National Quantum Mission and AICTE, together DST and AICTE, started the MTech program in quantum technologies for all the AICTE approved colleges. So both BTech minor and MTech programs, which were started originally at IISc, is now there for 9,000 colleges across the nation, whoever wants to do that. So there's a lot of opportunities in quantum, and this shows how important quantum is becoming. And this year, we just approved the colleges. DST is going to give out about close to 100 colleges resources for building quantum laboratories. And because quantum laboratory, unlike many other, is not a very cheap thing, because there are certain very specific equipments you have to buy. And as a result, one has to have appropriate resources for that, both software and hardware. So DST is giving that, and with the first tranche of colleges just been approved. And in the next few calls, we hope nearly more than 100 colleges across the nation will get the resources to start their quantum laboratories. Okay, good. So with this, let me get started. As I'm going to give a little bit of conceptual understanding, but mostly this will be a bird's eye view, because I saw the program that you have over the next 2 or 3 days. There are a lot of people who will go into the detail or the depth of the whole thing, but we'll get started from a little bit broader view. Before I start, how many of you have seen quantum physics or know a little bit of details of the quantum technologies? Let me just see a hands up. Okay, good. So, we have a sizable portion of people who have got a little bit of quantum exposure. I'm going to tell you a little bit about what quantum physics is, although if you take a look at, let me see. Sorry. So this is Richard Feynman. He said a long time back that if you think that you have understood quantum physics, then you are strongly mistaken. You probably do not understand quantum physics. Well, this is where we start from. Okay. Let me just see. This is. Oh, okay. I think I know. I have to direct it like this. Huh? That's okay. Yeah. I got it. It's just that the direction has to be this. That's it. Okay. So this is originally about one of the reasons 2025 was the International Year of Quantum, is because about 100, now a little bit more than 100 years ago, Erwin Schrödinger came up with this Schrodinger's equation. It was published in 1925, which started what you call the first quantum revolution. The Schrodinger's equation, which is essentially the Hamiltonian of operator working on a state vector psi, gives rise to a wave nature of the nanoparticles or quantum particles in a solid, and or any material as such, which led to the start of what you now call old quantum. Although last 100 years we never called it old quantum, we called it quantum. Okay, what it did is, of course, it says that okay, we understand the properties of all matter, and quantum theory is one of the most successful theory in the history of human science and technology. It still has, we have still not found any experimental evidence which says the quantum physics is not correct. So it's one of the most successful theories in history. And the problem is that it, in addition to giving some clear descriptions of matter using quantum states, it also starts giving something weird, something hidden, something more non-trivial, and that's what makes quantum technology today. Okay, so for example, in this way of looking at quantum, we now know we know why silicon is a semiconductor; it opens a band gap. We know why gold is a metal which has got conductivity, high conductivity. We know metals and insulators. We understand molecules, so on and so forth. So we understand quantum world around us with quantum physics. And after 100 years, we are now in a position to engineer our understanding into technology. So this is the first quantum revolution, started about 100 years ago. And this is something which Richard Feynman started. I mean, people attributed to Richard Feynman in the 1980s, saying that, okay, it should be possible to simulate a quantum system by another quantum system only. And this is where the whole thought process that can we make a computer which can simulate the quantum world, that started coming in. Okay, so what we understood very soon is that if I understand the science, now that we have got about 100 years, and we now start engineering it, then we can start getting devices and systems which is a very, very different type. And we use these, in addition to the understanding of it, we start using the hidden properties of quantum, which is three hidden properties: the entanglement, superposition, and measurement. I'm going to give you a little bit of idea of what they are. We can now create devices which are of disruptive functionality, extremely high sensitivities, and speed, in many, many cases, speed beyond the classical technologies that we use today every day. Okay? So today's quantum technology is based on three different areas. First is quantum computing, a new computing paradigm which leverages the laws of quantum mechanics to provide significant performance enhancement in certain classes of problems. I don't think we have understood or know yet what quantum computer can do. In fact, I'll show you at the end. I mean, we didn't do that even when the classical computers came back in the mid-1950s or so. So we don't still comprehend the impact, but at least we know there are certain aspects which can be quite dangerous in some forms that the computers can do. But it's certainly not the only, and this is one of the major mistakes I see wherever I go. Whenever people talk about quantum technology, they start immediately saying, oh, quantum computing. But that's not true. Quantum technologies have got three different components. One is quantum computing, other is quantum communication, and the third is called quantum sensing. Quantum communication is essentially a secure transfer of information that you can identify if someone is hacking and immediately before and the system is going to get irrevocably modified. Okay, and the third is quantum sensing, and this is a new generation of sensors that again based on those three core aspects of quantum physics, that is entanglement, measurement, and superposition, and provide measurements of various quantities like electromagnetic field, gravity, rotation, time, for example, are orders of magnitude more than the classical sensors. So this is extremely important to understand. And what is more important to understand is that probably as far as the marketability of quantum technologies is concerned, quantum sensors are probably going to hit the market much, much sooner than quantum computing. Probably they have already started coming in. I'll show you a couple of examples of that. So quickly, a little bit of classical versus quantum computing. We know a classical computer is classical bits. In a quantum computer, we have quantum states, the psi that we talked about, right? Now, there are two vectors. With two vectors of up and down of quantum state, we, in principle, can describe all possible states of a quantum system. For example, if you take a look at, this is a quantum bit. A quantum bit is composed of the two state vectors, and a superposition of these two. This is the superposition, this one, where a whole quantum state can now exist in all points of this sphere, simply by taking alpha and beta as the projection of this vector on different planes of the x and y coordinate system. So for example, when we have a system psi, then I do a measurement, and this is one of the critical aspects. This is where it led to various other alternative interpretations of quantum physics, like is the current interpretation correct or not, but we will not go into those philosophical questions. But what quantum theory says, that my system, as long as I don't see it, stays in the state of superposition, but the moment I measure it, it collapses into one of the states. Either it collapses to the up state, or it collapses into the bottom state. Okay? Till then, this is why Einstein didn't like it, right? I mean, Einstein and Bohr were walking around, and this is a very well-known story. And then Einstein says that are you saying that the moon is behind me is not there because I'm simply not looking at it? And that's the philosophical challenge that we have to agree to live with. It turns out that we don't have the entire description of reality. There are a lot of things that are happening that we don't understand, but if you agree to continue with it, then we can make technologies today. Okay? So we can actually, by simply changing the alpha and beta, because it is alpha and beta are continuously varying numbers, you can put the state vector anywhere you want. It can be along any axis, and it goes on. But the point is that unlike the classical computer, where the silicon plays the crucial role, in quantum that is not the case yet. And this is what this talk is going to be about. It now has photonic processors, superconducting processors, semiconducting processors, neutral atoms, trapped ion. There are various different platforms in which people are trying to generate this two-state system, which is measured up and down state. Okay? Right. So how does one create a qubit? Let me just, this is at the start. If you want to do quantum computing, you have to have a qubit. So this is a typical superconducting qubit. I'm going to give you one example, but each platform that I just showed you have their own way of creating a quantum two-state system. So this is a transmon qubit, in which, after all, this is about original one. It's a 3D cavity of about 2 by 7 millimeters square. And then here we have two superconductors which are separated by an oxide, and this is what is called a Josephson junction. Okay? It turns out this Josephson junction is a unique system because you can model it as a nonlinear inductor, right? And when you have a capacitor which is in parallel with the Josephson junction, you get what is called an anharmonic quantum LC oscillator. And when you have an LC, simple harmonic, those of you who have seen quantum mechanics at some point, and you know the first problem you solve in your bachelor's or earlier is the simple harmonic oscillator problem. In a simple harmonic oscillator, you get an equal energy space because your L is independent of energies. But in this case, L is not so. It's a nonlinear oscillator. As a result, the energy levels are unequally spaced, and this is what is called a physical qubit. At the lowest two is the states for my quantum two-state system. The system can exist in either this state or in this state, and the distance, the difference between those two states is usually about 5 to 50 microelectron volt, which is approximately 0.2 to 2 Kelvin temperature. And this is why, in order to run a quantum computer on this scale, we need very low temperatures. You need cryostats. What you saw in QPA AI, the cryogenics, the 10 crore system, which I'm going to come to later in the lecture, that cost is 10 crores. But if you want to make this, which we make this all the time in the laboratory, and if you have an infrastructure of lithography, this probably will cost you about 1,000 rupees. Rupees is what I'm talking about. So you see, the making the quantum hardware itself is not very difficult. It's cheap, but maintaining it in the right atmosphere is far more expensive. It's actually much beyond that. I'm going to go step by step as we go along. Okay. So I'll give you a little bit of idea. If you create a qubit like this, what is so interesting? Why people like Einstein, people like, why the whole community, when the quantum mechanics was getting born, what was the fundamental challenge? And that actually led to 2 Nobel Prizes in the recent years. First is that, okay, I told you this, I'm going to quickly show through. This is a typical quantum circuit that it looks like today. And then this is the cryostat that is 5 to 10 crores of rupees, which keeps the quantum circuit at low temperature. But then you use radio frequency pulses, which makes a qubit state go to different superposition states. Alpha and beta, they keep on changing depending upon the number of pulses, duration of pulses that you apply, and those pulses come from the room temperature. Okay? So that's how a quantum computing is done. Okay, so this is interesting. Now, what I wanted to talk about, suppose this is a concept of entanglement. I'm sure this is one of the most difficult concepts to fathom if you are a quantum physicist, or even if you are not a quantum physicist. As far as entanglement is concerned, I don't think I understand even one atom more than what a completely non-specialist would. But this is the effect. Suppose you create an entangled 2 qubits, that means 2 pairs of states, okay? And you entangle them quantum mechanically, and you then send them very, very far away. One goes to Mars, other goes to Jupiter, okay? And you've got 2 people sitting in 2 different places. One is Alice and other is Bob, so that's usual. You can always give Indian names as well if you wish to. But the point is that suppose these 2 are not knowing each other, they are very, very far away, arbitrarily large distances, but then they start measuring these entangled qubits at their own locations. And they will measure 1 qubit, it comes, the system is an upstate, downstate, downstate. So series of entangled qubits, when they reach those individuals, they measure it. Remember, they don't know each other. Okay? But then, if someday somebody starts, hey, Alice, what have you got? And Bob, what have you got? And you'll find that they are perfectly correlated. Even though their measurements at their individual locations were completely random, the same entangled qubits, if they measure, they will measure something exactly which are completely correlated. And essentially it means that as if the measurement of Alice somehow impacted the outcome at Bob's place. Now this is the action or a distance that Einstein didn't like at all. And how can some information can travel instantaneously over the arbitrarily long distances? And then in 1935, he came up along with Boris Podolsky and Nathan Rosen, saying that there must be something wrong, and we came up with what you call a local hidden variable theory. And that sort of, Einstein was a very powerful man, and it continued for many decades. And somewhere around 1964, John Bell, who was working in Bristol University at that point, came up with a strategy from which you can distinguish between Einstein's EPR paradox, it's called a local hidden variable theory, and the quantum physics, and came up with this Bell's inequality criteria, in which he said that if some correlation bound inequality or parameter, if its hidden variable theory is correct, then that parameter will be 2, but if quantum theory is valid, the parameter will be 2 root 2, slightly larger. Okay? And then the experimentation started. And it took another 40, 50 years for these two gentlemen, these three, Alan Aspect, Anton Zellinger, and John Clauser, to come up with quantum optics experiment that showed it is more than 2 in all experiments that they have conducted. Essentially saying that the Einstein's view of reality through local hidden variable theory is incomplete or incorrect, and it is a reality, whatever it is, that quantum theory says is correct, and for that they got the Nobel Prize in 2022. So now it has become a global race, and it's only topic, I believe, which got 2 Nobel Prizes within 3 years of period. That is the 2022, these 3 gentlemen, and 2025, although John Clark, Michel Devoret, and John Martinez got the Nobel Prize because of a work that they did in 1980s that has led to the superconducting quantum processor that I showed you today. Okay? Today's dilution refrigerators look something like this. The number of wires that come out is unbelievable. I'll come to that in a bit. But this is how the quantum theory has expanded. So one of the problems is what are the different origin and performances of different qubits. I showed you about the transmon qubit. But if you look at today's platforms that people are talking about to make quantum computing, there are the sizes of qubits actually go over 6 orders of magnitude. That is, this is transmon qubit in the orders of millimeters. But if I look at the vacancies in diamonds, which are just about 1 molecular distance or atomic distances, 3 nanometer or so, then we have semiconductors are coming in a big way, the shallow donors, then the silicon quantum dots, the gallium arsenide, these are in the order of hundreds of nanometers, the size of a quantum 2-state system. So if you want to have 1,000,000 qubit, and I'll tell you why we need 1,000,000 qubit, then we have a realistic chance of putting them in the same cryogenic system. Otherwise, if you see a 10 millimeter and I want 1,000,000 of them, you need a cryogenic system that is 1 kilometer size, which is very difficult to get. Then we have trapped ion. This is about a micron, so a few tenths of microns. We have photonic qubit, which are all similar orders of magnitude. So this is a very large number of processors spanning over very large distances that people are looking for in quantum computing. Okay, so comparing qubit technologies, which is why this is, look at the number of companies that, and which are giving in, and these are serious companies who are still betting their money on their own technology. For example, IBM, Google, Rigetti, they are saying that, okay, this is superconducting qubit, although we have high gate speed and fidelities, the problem is it needs cryogenic cooling, and also right now the problem is coherence time, it's very noisy. Then we have superconducting qubit. You can see Intel, then Dirac, these are big companies, Silicon Quantum Computing. They are saying that, oh, it's not superconducting. We'll make a quantum computer based on semiconductors because we already have semiconductor foundries making our computers, so we can use them. Although the problem is that even this also requires cryogenics, but it's very, very difficult, very low coherence time, even lower than the superconducting qubit. We have trapped ion qubit. This is probably one of the most promising in today's context, give and take. There are opinions of different people. IonQ, for example, Quantinuum, they have got extremely high fidelities, extremely low noise qubits. Okay? I'm going to show you what makes it more interesting. But they are very slow. You see, the problem is that there's always a trade-off. There are superconducting and semiconducting qubits are much faster in terms of gate response, but ion qubits are much slower than the other two. For example, neutral atoms, advantage is that it doesn't require low temperature. This also doesn't require much lower temperature, but the long coherence time is very good, but the problem is that it needs higher vacuum and extremely sensitive to the lasers which trap the atoms and ions in an appropriate array. So that is the bottleneck. And extremely difficult to know today's technology. How will you make lasers so accurate and so low noise that we can make millions of atoms or neutral ions array in a particular way? And finally, photonic qubits. ISC is going to do a lot of work in this. One of the advantages is that photonic qubits work all at room temperature. There's no problem. although the detectors are still at low temperature. But the problem is, there are noises and photon loss. Each program requires own chip and various other chips. But still, look at the number of companies that are investing in that. So these are right now the overall global landscape as far as the quantum computing is concerned. Question that you ask is that, okay, they are all doing good, but question is, how many qubits do I really have to have in order to make a real impact? I mean, why people would, when people say, aha, now I'm in serious situation. Okay, so first of all, to make a practical quantum computer, one requires to correct errors and make logical qubits from physical noisy qubits. What I showed, the two-state system, is a physical qubit, but they are immediately prone to electromagnetic fluctuations. They lose their quantum informations very quickly. So you need to find ways in which our computers work. You press a 1 + 1, it always has to give 2 without any fail. So we have to make logical qubits. Now in 2012, one of the major directions it was recognized that the way our bank accounts and various other information is encrypted was at that point of time called RSA 2048. Okay? Essentially, the asymmetric encryption mechanism, which public and private key pairs which was expected to be safe till 2030. That was the idea at that point of time. And people used to use RSA 2048 as essentially a product of 2 prime numbers, each of about 2000 bit long. Okay? And it was realized that a quantum computer can easily search for that and realize it. So question was at that time, 2012, that how long will a quantum computer take to break through an encryption of this size? And if I estimate that, so you have to factorize a 2000-bit quantum processor or a number, and we need about 4,000 logical qubits at that time, because there are two such numbers. And then in order to convert a physical qubit into a logical qubit, at that time, it's about 12 to 13 years ago, the quality of the qubits were not great. So you needed a lot of physical qubit to make a logical qubit. At that point of time, the estimate was about 14,000 physical qubit used to make one logical qubit. And from there, it was estimated you need about 1 billion physical qubits to make a quantum computer that will break the RSA protocol with Toffoli gates in about 26.7 hours. It was impossible to do so within classical resources at that point of time. Even today, it's not possible. But with a quantum computer of this size, of about 1 billion physical qubits, having about 4,000 or order 1,000 logical qubit, we can break the RSA protocol and get into the security within about a day. Okay? But look at the situation today. So the question that I want to ask is, evolution of qubit technology and algorithms over the years, when will the quantum computers break classical encryption with today's technology? When they do that, that's called a Q day. By the way, there's a name called Q day. Okay? A Q day is a day where we need a whole different PQC protocols. Of course, PQC is working very hard to make it quantum safe, even if you have a quantum computing of that size. But nonetheless, from technology viewpoint, let us see what happens over the last 10, 12 years. So this is the number of physical qubits, and on this I have got years. Okay? This is essentially the industry roadmap. That means we have where industry has said our physical qubit will be, and this is the projection. And this is roughly, this white one dot is how much we really achieved engineering-wise. So you see, what we can say that our engineering has been pretty good, and it is following the industry roadmap more or less at the same time. And that probably will continue at least to a little bit, I mean, although I'll show you a little bit later at the end. At the same time, the algorithms to break the RSA protocols have also improved. And our goal is now not the original 2012 1 billion qubit, but even today, we know we can do this within about 10 to 20 million qubits. So the algorithms have improved as well. Okay? So now if I look at the qubit technologies and various platform, ions, superconducting, this is where we are. say, if in order to have 1,000 logical qubit, this is our goal to break the RSA protocol, 1,000 physical qubit per logical qubit is enough in the superconducting platform. And the other platforms, say for example, just 10 physical qubit over a logical qubit is enough for, say, trapped ion and cat qubits. We believe that this leads to a range of possible date of Q day can be anywhere from 2027 to 2035, around that. So we really need to get ready. We need to get ready with our quantum computer and the PQC protocols well before that, because otherwise this is a serious national threat. Okay? This is why many of the countries are working towards this. Okay, so good. So this is why we are here, right? I mean, this is the purpose. So if I give you an idea about different companies, where they are and what their projections are, you see IBM and Google say that 2026 they have 1,000 plus physical qubits. By 2029 and 2033, they will have 1 million qubit, about 2,000 logical qubits. Google has a similar kind of, Google has more ambitious plan. It says by 2029 they will have 1,000 logical qubits ready. At the same time, if you take a look at, QERA, the neutral atom qubits, by 2026 they said 100 logical qubit. By the way, I know I gave you the impression that the quantum computers are only break our bank account passwords, but that's not really true. Quantum computers can do much more than that, and this is where I'm going to come in. And even 150 logical qubits actually will affect DFT calculations, material science, optimizations in a serious way. So there are a lot of things that one can do as we make better and better quantum processor. Okay, so even INQ says that they will make something which is quite, they have a different architecture, but anyway. So these are industry roadmaps today. See, the problem is not easy, and I'll give you a feeling of the problem that we have in making a full-scale quantum computer, right? So, for example, today we are at 100 to 1,000 physical qubit level, okay? We have, the problems we need to solve is how to make better quality qubits, so that my physical to logical qubit conversion doesn't require too many physical qubits. That's a major, the quality of the qubits is most important requirement today. Then our next phase is going to be 1,000 to 10,000 qubit processor. There the problem will be the wiring and packaging issue. How can you make and put all 10,000 qubits under one cryostats? How to ensure that those qubits, because they are continuously working at the radio frequency pulses, how do you make sure that they don't talk to each other? As a matter of fact, if you take a look at the typical 150, 160 qubit computer, which Andhra Pradesh government just bought from IBM, typical cost of making such a computer is about $5 million, of which really the quantum component and RF, etc., equipment components or material component cost just about $1 million. $4 million out of $5 million goes in wiring, the cost of wiring, the various kinds of wiring that will allow you not to make quantum components talk to each other, the crosstalks and various, the small isolators, the circulators, filters, so on and so forth. Okay? So that's going to be the next phase of challenge. The third phase of challenge, and now we are getting closer and getting warmed up, really doing something of useful, is about 10,000 to 100,000 physical qubits. And there the challenge will be the circuit level challenge. Okay? The circuit level challenge is the verification, testing, debugging. In many cases, you run a quantum algorithm, whether the answer is right or wrong, that is not very easy to determine. It's not a classical computer that you are almost certain to get in various ways. Quantum computers, the outcome of quantum computers is not testable in standard ways. So we need to find ways to debug our circuits. Error correction codes to reduce fault tolerance overhead, right? I mean, you need much better error correction code when we are looking at this type of circuit level challenges. The final destination with all these is when we really hit the 1 million. And we are almost certain that it will no longer be a one computer sitting under a dilution, it will be distributed quantum computing. It will have to have different quantum processor where we need quantum interconnects. And now the complexity comes at the system level complexity, right? That is challenges due to quantum interconnects, dependability and convergence of effective microarchitecture, and we probably will have to develop what is called a quantum operating system. Okay? So this is more or less the pathway from today to maybe 5 to 10 years' time, and we need to be ready about all these infrastructures step by step in its own detail. Okay, I have to say that quantum communication, very quickly, quantum communication is, after all, a communication mechanism that doesn't allow you a hacker in between, and usually there are various ways. You use single photons and use single photon properties, for example, number or polarization, to which is a quantum property, to communicate between two parties. And one party starts with a single photon, and then other party detects them and compares their polarization. And if there is a hacker that comes in between and changes the polarization of one photon in between, then immediately the correlation between that I talked about gets destroyed, and you know there is somebody who is listening to what you're talking about. So that's fundamentally quantum mechanically robust mechanism of securing information transfer. Okay? And that now will have series of effects. For example, making integrated quantum cryptography, then eventually going to the quantum internet is where we would like to eventually go. Finally, the third one is quantum sensing. There are many areas in quantum sensing now is being looked at. For example, making magnetometers with extremely tiny, and this is where it goes to the social structure, with diagnosis, civil and defense, medical, as well as optimizations in various forms. Quantum sensors will have an immediate and deep impact on our quality of life. Okay? For example, atomic magnetometers, these are magnetometers which will make, say, MRI machines where we have to go inside the magnet, whether we can have, MRI is just like a helmet, essentially, handheld MRI machines. You just have to go around it with your head, and we know the imaging of the brain. So these are areas where we would like to see, and there are people are already working towards it in making quantum sensors. So for example, on that note, look at the magnetic sensitivity that we are looking for. This is where our standard magnetic sensitivities are as a function of sensitivity and the size of the magnetic sensor. So you see, this is the goal with extremely tiny sensors with extremely high sensitivity. This is where we want to go, and now quantum systems like the diamond in vacancies in nitrogen vacancies in diamond actually starts this size and extremely high sensitivity. It is going to come down to about picotesla. Here, within the lifetime of the National Quantum Mission, which is about next 5 to 6 years, we will have new solutions to magnetometry. Okay, you can see this is an example of a gravimeter, or which measures the vibration of the Earth, tectonic plates and various volcanic regions. Mount Etna in Sicily, in Italy, is a vibration-prone zone, right? And there, these things actually can measure much lower vibration of the Earth crust, which can lead to much better modeling of tsunami, earthquake, oil and gas exploration. So this is where quantum sensors are becoming extremely important. And then you can't leave out aircrafts. One of the areas is to make measurement of magnetic fields. I told you, so accurately that I can actually measure the variations in the Earth's magnetic field with very, very low noise. And if I do that, actually, while it's very good in many possibilities, but it also can be dangerous, because I can make magnetometers and guide or navigate aircrafts based on simply the local fluctuations of Earth's magnetic field, rather than communicating with the GPS through satellites. So I can now have way to navigate to areas which are GPS denied, right? So this has immediate impact on national security, warfare, and various others. So almost all products of quantum technologies are what you call dual-use products, which means they can be used for public good and they can be used for defense and strategic purposes. So now these are commercial products. This is the Q Control is a company which makes these tiny products. This is Sandbox AQ. These are products which are now loaded onto the aircrafts, and these aircrafts using AI and quantum, using quantum as the hard data and AI to reduce the noise or model the noise. These are products which are now being sold to different, but these are not sold to different countries. You have to understand these are extremely, these are products which are strongly sanctioned. Okay, so key industries that we see within about 10 years or so, we are looking at an economic impact of quantum of about $1 trillion, of which major one comes in finances, about 400 billion. These are talking about, various settlement optimizations and financial crash estimations, and these are the areas. We have healthcare, where I showed, medical diagnosis as well as mRNA structure or predictions and various other very good things that one can do. We have telecom optimized network transformations, network traffic optimizations. We have material, and one of the major areas of application of quantum will be in material catalysis, quantum simulations, molecular docking, and of course transport, aerodynamics, traffic flow optimization. Bangalore could use some here. Then we have precise timekeeping, and these are the areas where we see the main areas where quantum technologies are going to have an impact on. We talked about AI. This is an emerging area. Quantum technology is going to impact and get impacted by several of the cutting edge technologies. One is AI and machine learning, robotics, sustainability and climate tech, as well as cryptography and cybersecurity. I want to spend one slide on AI and machine learning. It will be good to have a little bit, there's a lot of, I have a separate talk on that, but I don't think I have time for today, but I'll just give you a glimpse. So AI and quantum are essentially complement to each other. Both are the ways in which they can help each other. Okay, potentially trigger transformative breakthroughs from healthcare to cybersecurity, but could also exacerbate existing social issues such as job displacement, etc. But the bigger problem is that AI and quantum can produce something which we may not have any control on. But that's not the reason why we should not do this. So first is, of course, how quantum technologies can help AI, that is, quantum for AI. This is the first one. And there are 4 or 5 areas in which quantum for AI. Quantum, you will have a course or lecture on quantum machine learning. So that's essentially quantum for AI. Essentially, algorithmic efficiencies, quantum algorithms could enable more efficient AI training protocols, and that is through quantum machine learning. The memory size, for example, as AI and Gen AI models get larger, the memory in classical GPUs are no longer enough to store the models. So you will have much more efficient memory storage. Similarly, the compute power, one of the areas that's certainly going to get affected is that the compute power to train the largest AI models is growing exponentially, but the classical computing power is not growing that fast. So the way to do that is to have quantum processors come in, which will essentially have the exponential growth of the large AI models training. So we need quantum processors to use for the training purposes of the model training purposes. So this is for quantum computing for AI. The other side, the AI for quantum computing, is as important. For example, there are 4 or 5 different stages at which AI and quantum will come in. For example, quantum hardware and design. AI can give us better superconductors for superconducting technologies, for example, through material design. Software applications, AI can support the development of optimized quantum code. Then we have hybrid integration. Almost all what I see when I talk to experts now, it is almost certain that quantum hardware will come in HPC quantum QPU, high performance computing and quantum processor unit hybrids. That's our immediate goal, and essentially load a lot of data onto the quantum processor, gets the outcome, and then process it for AI purposes. AI can actually help us in error correction because the noise, I already showed, one of the perfect example is noise mitigation or reduction in quantum sensors, for example. So there is a huge amount of complementarity that each of them can use. Okay. So if you see the investments in quantum technologies and AI, it's very interesting. So if you look at the investments that have happened over the last few years in AI, the global investment has exponentially increased from 2022 to 2024. Quantum investments have remained flat, but if you look at over the last 2 decades, the deals, the VC deals in quantum and AI are essentially parallel to each other, just separated by about a factor of 10 years or so. So we can clearly see AI and quantum are moving together in a common goal. What are the challenges? Now I come to about next, how much time do you have? I started around 11:10. So do I finish at around say 12:05? Is that okay? Okay, so about 10 minutes or 10 to 15 minutes. That's enough. Okay. So what are the global challenges today? And this is something which we must be aware of when we are working in quantum. For example, there are human rights issues. I will not go into that. Collaboration. And this is something which is going to be far more tricky than our previous academic collaborations that we have had with countries. Quantum being a dual-use technology, it can immediately affect our collaborations with global universities, and almost everywhere there are MOUs which require special attention to quantum technologies whenever we want to write an MOU with overseas universities. It could be even more because there could be visa restrictions for quantum scientists or technologists from one country to the other. So this is already being discussed. Policies, how to handle this, we don't have a very well-defined policy on quantum. And, technology standardization from one country to the other is also an open question. As a result, if you take a look at this is 2024, multiple nations are giving strong export controls on quantum products. And if you don't believe me, this is 2025 update. Last September, EU has now exercised control related to components on quantum technologies like computers, electronic components like cryogenic temperature, parameter signal amplifiers, cooling systems, wafers, etc. It's now going to get increasingly difficult to getting them imported from somewhere. So one of the important things is that if you want to have a strategic safe, then quantum technologies must be created within the country. This is not a semiconductor technology. This is not computer. You cannot buy anymore a computer that we can, okay, let's have a large computer, we'll do all the calculations. That's not possible anymore. And as a result, we need to look at what are the technological adoption challenges for this country. So first of all, we have a problem of private funding problems, and I'll give you some data on that. And although India produces largest number of quantum-trained undergraduates in the world, our technology output is very small, and this is where this community is extremely important to nucleate such large-scale quantum education in the system. Then we have the problem of manufacturing of semiconductor. This is one of the key challenges, and the regulatory and the governance aspects. So that's more technical. Okay, so let me give you a little bit of idea about where we are in terms of investments. You see, I talked about private investments, right? Look at this. Overall, today, about $54 billion have been invested by the federal governments of different countries in the world. India is here, okay, about $1 billion. The circle size is the amount of investment that you have. China has invested $15 billion, which is very large, okay. But if you see the amount of investment India has done from the governmental perspective is not too bad. It's quite respectable. Okay, but now let us look at the private funding vis-a-vis the government funding in these different countries. What I've drawn here is that this one, the blue one, is the government funding, and the red one or the orange one is the private funding ratio to the government funding, which means in America about $3.5 billion or $3.8 billion have been given by the federal government in quantum related activities. The Googles and the Microsofts and the IBMs, if they get added up, their own investment is about $4.2 billion. So that is more than the private funding. Similarly, if you go to Europe, this is the same thing as Canada, and Israel also is much larger. If you look at Europe, it's more or less between 5 to 10%, with UK as the exception. About 35% of the total of the government investments comes from the private resources. Asia is also something about 2 to 3%. Coming. Here is India. In India, this number is 0.2%. And this is a big worry, that our industry is not being either supportive of or have the confidence in us that we can deliver this technology, or they are simply looking at returns which are of very, very immediate nature. We do not have, so they are not probably seeing business, which the American companies and other companies are seeing that they are making revenues. The quantum computing companies like IBM, like Amazon Web Services, their revenue is increasing at 40% today, and it will cross $1 billion from quantum computing services today. It has crossed in 2025. Somehow we are unable to see business in quantum, even though we know tomorrow we will not have this business because it will be taken away because of strategic reasons. Okay, so this is something which I want to talk, and I want to also show the quantum. If you see, India today produces the largest, apart from EU, it produces about 100,000 quantum educated graduates every year. But if you take this is, as a country, is the largest in the world, and even larger than China, by the way. But if you take a look at the number of patents and products that we have, it's about 2% of the papers and hardly anything in patents. This is patent. Okay? So we are really not producing technology. Somehow all these graduates who know quantum are getting lost and going to some other disciplines. And we got to do something about that. And I think this is where this community can help. Okay. So how do we solve this problem? We solve this problem by creating clusters. And this is what the approach that the Karnataka government is taking. I'll show you there are now quantum clusters, which essentially means that a holistic quantum system where you have 5 key enablers. Enabler is capital investment. Quantum is not cheap by any means, okay? But we have enough. Indian government has already given that money. Karnataka government is giving 1,000 crores or pledged 1,000 crores. We just have to have people from private sectors to come up and help. Okay. Then we have physical infrastructure, laboratories, quantum facilities, foundries. We have that in ISC. We have got several institutions across academic institutions. QPI AI has its own foundry today. We have academic institution, and this is one of the crucial aspects where Karnataka as a state probably holds a very important edge. Karnataka has 5 academic or 6 academic institutions, Bangalore alone, which is almost impossible to find in any other big city in India. And quantum is in a state where you have to have academic institutions, and government and private sector must come together, because none of the technologies in quantum is absolute final. This is not silicon processor that we know how to make an electronic device. It is still evolving. And it's only through a continuous engagement with academia, government, and private policies that we will be able to get there. So for that, high quality people, of domain experts, ready availability of domain experts are required. So which is why the academic institutions are very, very important to have in close by, and which we have. Industry-government partnership, and finally, accessibility and integration. You got to make the infrastructure that you make accessible to everybody. Small ideas needs to be products, okay? So these are the 5 key enablers with which many, about 20, 25 clusters in quantum world that are now distributed. Chicago Quantum Exchange is a perfect example. It promises you, it promises economy of nearly $100 billion, about 80 to plus 20, about $100 billion by $80 billion by 2035. It's going to create about 191,000, 2 lakhs jobs in quantum and various other areas. So these are the typical, and look at the area that they have. It's nearly about 225 miles in the Chicago area that's one such example of a cluster. Okay. What does a cluster do? It actually looks at quantum technology in the quantum stack, in which you start from the quantum material, you fill up all these components, whether it is a single photon detectors, whether it is cryogenic amplifiers, whether you have softwares at the same time, and then cloud services and provide logistics simulations and various other things. It is not about buying a computer and making only this one. Then that is not a sustainable quantum cluster. So in order to make a quantum ecosystem, we got to enable all aspects of quantum stack. Now this is what we would like to do, and this is what Government of India wants, and this is what Karnataka Quantum Mission is about. Since I'm here in Karnataka and have been closely associated with Karnataka Quantum Mission, let me show you a couple of slides of where we are and what we would like to do. Our Honorable Bosarajuji has driven this for, and taken it to a different level, as well as ITBT Minister Khargeji. So we would like to have a sustainable quantum cluster in Karnataka and the Quantum City project, where we would like to have, and why this is a very good place is because it is the largest information technology. We have already a fantastic innovation culture and some of the best institutions. We also have a deep tech. There are 5,700 deep tech companies, startups, for example, in this area. And finally, we have this government commitment now with both land and money on the table. What shall we do? We shall start giving services. You see, we are looking at a quantum stack, so we should give services. So it will be a multi-platform services at this stage, simply because we cannot afford to give services just by making a superconducting quantum processor. Tomorrow's scalability of a superconducting processor can become questionable. Maybe semiconductor will become better. So there is now going to be a fab line in the Quantum City project. And these services will then reach out to both Karnataka and outside through quantum data centers. Okay. Facilities and infrastructure. We need to have infrastructure that will make a quantum foundry possible, making quantum products under a common roof. We need to have manufacturing in there. Manufacturing not for research, but for product, commercializable product. Okay. We have a whole startup ecosystem around this manufacturing and facilities. We have to have skilling and outreach. Of course, looking at the human resource generation is going to become absolutely important. Okay? And finally, of course, export. And this is something which hopefully will add an economic benefit to the community at large. Okay? So this is our approach going to be. And one of the things is that how to bridge the supply chain. In India, this is one of the biggest problems. For example, we have the core quantum product called a quantum circuit. And this is something which we have 2 or 3. Even IISc has a quantum circuit where there are superconducting quantum processor. We have 4-qubit quantum processor running in IISc. We have got 6-qubit quantum processor running in TIFR, Bombay. National Quantum Mission, if the mandate goes in next 5 years, we have 100-qubit quantum processor running. This is core quantum product. But the problem is there is a whole associated is quantum associated product. For example, the cryogenics we just talked about, 5 to 10 crore of each investment this. We don't have any company in India which makes dilution refrigerators or cryogenic systems. Okay? And then we have beyond quantum product. That means products that you start making because you have a quantum application in mind, but the outcome of those products will go well beyond. For example, drones, the microelectronic circuits, for example, can not only be used to send pulses to dilution refrigerators, but it can also make fantastic microelectronic circuits for consumer electronics, for drones, for various other strategic applications. So that goes beyond quantum products. So we are trying to make manufacturing as one of the major areas where we should concentrate. As a result, if you simply take a look at one product, I'll just give you an example here. So a dilution refrigerator which carries quantum signal will have these filters. This is called radio frequency cryogenic filters. If you want to buy one filter from the market, it costs about $384, which is about 25,000 rupees. A dilution refrigerator, just one, will have hundreds of them. So imagine the amount of business that we can have even by looking at peripherals or small components for quantum products. Even if those components have nothing to do, an RF filter has nothing to do with a quantum product, right? But it actually makes the quantum ecosystem. So typically in the last year or so, if most companies worldwide are actually looking at small components, you see equipment components, these are application software, these are the areas where the startups are developing. Okay. My last couple of slides. So this is overall economic impact that we see in about next 5 to 10 years. But if you want to get the return of investment much earlier than that, then we have to, so the quantum computer will be ready somewhere here in 2035, 33, 35, maybe earlier, I don't know. But if you want to get the return of investment earlier, then we got to find ways in which we have to couple the software and teaching, the algorithm, the material community, the microelectronics community, and heavy manufacturing community. Because those who can make lasers, those who can make pumps, those who can make thin film deposition units. So these are areas in which we already have expertise. It is just that this expertise doesn't know that they can contribute to the quantum ecosystem. So we need to create a structure. My last slide here is this. So what we do here is how does the quantum city will be building the ecosystem and engaging with technical workforce all over the place. For example, these are the core quantum technical workforce. This is quantum scientists, quantum engineers, quantum AI/ML experts, quantum startups, and core manufacturing. We would like to get the other side which are not quantum. For example, the communication engineers, mechanical engineers, polymer chemists, material experts, how do they can contribute to the quantum ecosystem? We need to find ways to give them information that these are the areas where you can contribute. And then we have to connect to the stakeholders, biopharma guys, doctors, surgeons, environmental civil engineers, and so on and so forth. So these are areas, this is how we are about to create the quantum ecosystem. I hope this is an ambitious plan, but it has to start from somewhere. BARC, ISROs, they started from somewhere. So I think we are at a crux of history where we believe in the next 5 to 10 years, our lives will be improved with the quantum technologies, but there are much more than that this ecosystem, both in Karnataka and India as a country, is going to get benefited. Thank you very much for your attention. Thank you.
LLMs are used for cyber security. If you can use and make the error as a threshold, maybe our efforts at going for higher things may reduce. Because in medicine, somewhere I saw.
Yeah, I think, many of the AI models are going to have a very strong impact on quantum technologies. It's just that one needs to have the right hardware, which then get benefited. And the problem right now is simply the availability of the right size of the hardware when it comes to AI/ML and quantum interfaces. LLM is just one of them.
Yeah. Sir, nanosensors, you told you are also specialized in that. Can we?
What, do you want to go back?
Yeah. No. We need not go back.
Okay.
General question only. Nanosensors for water quality is very important for us throughout India. So your filters which you are talking there, that is maybe another kind of filters you talked.
Right.
Those may be of great help for Karnataka if you can use them into that.
Of course. Yeah.
Thank you.
Absolutely. All the components that we can make from quantum are already being used in some way or the other in various other technical sectors. So I think this is where we can help the manufacturing.
That random measurement can violate the Benz inequality.
right.
Can we ignore the basis of measurement?
Yes.
Choice of measurement basis.
You
in
can,
BB84.
you have to, in the public key, you have to share the basis, no?
Yeah.
So the choice of basis is known to both A and B, the Alice and Bob.
Yes.
And then only you can measure. Otherwise, your measurements will be uncorrelated anyway.
Correct.
So you need to have in the public key, you need to share the basis information.
Okay, that
And
is
then-
later.
that's
Randomly we
later.
can measure, but
Correct.
later we can share the basis.
Correct.
So in BB84.
That's correct.
Thank you, sir.
Yeah. Yeah, this question there. Right, right. So I think you have to, so data science as such is about training large models with data. So it's a data processing. It is not very clear how the decision takes place. Of course, there are classifiers and various other models. Now the quantum is built on a slightly different principle. But they are not totally independent in the sense that if data science is more of sorting data, quantum is more about generating data, in which you get either sensors or produce high quality data for your data science to take place, right? Today, if I get a sensor which operates at much better frequency, better sensitivity, it naturally provides much better predictive models from the data science AI models. So that's essentially the first level of collaboration between quantum technologies and data sciences. Sorry, can you just use the mic? Yeah.
How would the present students, because if the quantum technology is the future, then where we see your AI, machine learning, and the data science is booming,
Right.
and the quantum technology is the future,
Right.
then without the data, we cannot get to the machine learning, and the machine learning is deep learning and your AI.
Yeah.
So how this quantum would knowledge, because
Right.
technology is what we need to upgrade every year, like at
Correct.
every moment.
Yeah, so I think it is wrong to say that quantum technology is going to replace AI. That's not going to happen. What I see is that today quantum AI and machine learning and various data sciences are coming up as a field to serve certain purposes. Soon the requirements will go beyond sustainable limit. The amount of, so for example, if the AI is a requirement of US alone, and the projection is to be trusted, they will need 8 nuclear power plants to support the energy requirement for doing all the computations for data sciences and AI. So that's not going to be possible. So you need to now piggyback with far more efficient and energy specific and more powerful hybrid models. So quantum comes at those levels. What quantum will do, quantum and AI will merge. And there would be collaborations in which AI models are going to get trained on quantum processing units. Quantum gives you the processing unit, right? Where multiple states give you much faster processing power, data management, memory handling, energy perspectives. Yeah, it will change the mathematical models as well. So it essentially means that you will now then require the AI engineers to load their data on a quantum processor unit rather than a classical HPC. Quantum data is no longer different from a classical data. We can talk about it.
Okay.
We can take 2 questions.
Sir, what is the decoherence in quantum computing? Like,
So the decoherence is essentially how quickly you lose the quantum information.
because it will affect with the environmental noise for the
Yeah, it
qubits,
is,
right?
absolutely, correct. And different systems have different rates of decoherence, different noise, which determines what is the good system to work. For example, superconducting qubits, they lose their quantum coherence in few hundred microseconds. So in order to do all the calculations, you have to do all the calculations within 100 microseconds. A trapped ion actually goes for seconds, for example. Okay? So there are advantages, but there are disadvantages also. One is slow, one is fast. So it depends on which platform you use, your decoherence will be different.
An excellent talk. I have a question regarding, it's a dumb question you can say.
Sure.
In quantum photonic chips, can we store the light, making use of
Quantum
this?
memories are supposed to do that, no?
The light,
Yeah.
light photons.
That's right. So the quantum memories are essential for this. What happens is the light comes in, and entanglement, they essentially goes in a medium which has got molecules which have got certain excited states. When the light comes in, they excite those molecules, and the light kind of gets stuck in a region for some time. If you can do a few microseconds also, it's great. Then you can use that to extract later. So this is the whole principle of quantum memory.
But won't it be the energy will be different?
I'm sorry?
The energy will be different, right? The
No,
excitation
it's
of the
not. You can generate the same information. So light comes with certain information. You later extract that information for a later use. And for that you need to get light confined in a certain region of space for some time. This is the quantum memory. Energy doesn't have to be different. You can actually have the same light source, same light output, same polarization, same entanglement properties.
Thank you, sir.
Thank you very much, sir.
Shall I? Okay.
Thank you very much, sir, for your scholarly lecture for 1 hour with a glimpse of the potential of quantum technology and also the global perspectives, so and also career opportunities. Thank you once again. I request all of them to please give sir once again a big round of applause. I request my colleague Umesh Gadki a small announcement. Please.
Thank you very much, sir, once again for your precious time and enlightening with us about the
Thank you.
fundamental concepts and global challenges and trends in quantum technology. Now we will be having a group photo followed by a tea break for 10 minutes, and after that we will be having one more session. So I request all of you to join us for a group photo along with the dignitaries. Thank you very much.
Excuse me, sorry for interrupting in between. I have observed in this speech, many people are holding mobiles and taking photos of the PPT. Okay, what we have in KST is YouTube channel. You can just type KST Academy, KSTACADEMY, and you can subscribe to the channel. Whatever happens here, it will come live there. Why I'm saying this? Because we have high-profile professors coming here. Those may not share the PPT with you guys. Those may share because of the knowledge share. Okay. So for that reason, I'm saying this. Please subscribe and you can watch.
Gave lot of suggestions, working out, structuring out the program schedule, and also some of the important key resource persons to organize this event. So thank you, Darshan, once again, and we heartily welcome you for delivering this lecture. Sure. Over to you.
Hello.
I'm audible, right?
I'm audible, right? Okay, great. Okay, before I start, I just want to understand all of you. How many of you here are aware of quantum technologies, have explored quantum technologies? Can I get a quick raise of hands? 1, 2, nice. Okay, so I want to keep this presentation and this window of space that we have to interact with you than just communicate what I know. Okay. Sorry, sir? Everyone can hear me, right? Great. Okay. So let's start with communication, which is the topic. Okay. So how important is communication in today's world? How important is security in today's world? How important is data traffic that needs to be secured in today's world, which is run purely by data, is what we are going to talk about. That is the core idea why I am in this field. And my company, ION-IA, a quantum research company, primarily works on quantum communication and cryptography. Okay, so how many of you are aware of banking and financial systems here? All of you. So what happens there? What does the data around bank and financial transactions involve around? Money, large scale money. And let's assume there is a huge data leak with respect to our governmental financial transaction. Does that create vulnerability? What kind of vulnerability? It's a national threat, right? It's a national threat. So today's encryption standards, which is the most said encryption mechanism of today? RSA. Why? Why RSA? Any of you? Why RSA? Yes, it's hard to crack. It's big. It's 2048-bit long. To factor it, how long will it take? How long will it take to factor it? It takes at least 1 billion years using our supercomputers too, because our supercomputers compute classically, not in a quantum approach. That is exactly why I am here representing a quantum approach to cryptography, a quantum approach to all these communication standards that we are building at IONIA. So the hidden crisis. Okay, in today's world, as Arindam Ghosh sir addressed, today we have very limited amount of qubits. Today the number of qubits that we can practically use is close to 1000, but they are all filled with noise. But let's say the amount of technological growth that we are seeing, the amount of new technologies that we are building quantum computers using, will exponentially increase the number of logical qubits, which will make it very easy to break our RSA algorithms. So the hidden crisis is here. Let's say today we just trust saying our data is encrypted. Is there any guarantee that if let's say like this, I give you guys a data, and I trust you guys that it's not leaked. And let's say there is an outsider who comes in and tries to, let's say he is an intruder who tries to access your data. Does any of us know in today's classical system if the data is being tried to be accessed by anyone? There is no mechanism. We just believe, we just trust, saying, we just trust. That's all. That is the whole classical system. But in tomorrow's world, or in today's, let's say, the dark net or some places, there's this quote, or they go by this phenomena that says, harvest now, decrypt later, because of the possibility quantum computers bring in. If they can harvest, if they can be the middleman, steal your data, even if it's an encrypted data, they can store it. Governments and agencies are funding almost billions of rupees just to store encrypted data, which is of no use today. No use today. But why are they doing that? Why are they burning resources? Because if they can harvest it now, 10 years, 20 years down the lane, every bit of that information is going to be used against the organization, against government. And that is exactly why PQC comes into picture. Okay, so you guys are all aware. I'm just brushing your concepts here. So AES, RSA, ECC, these are all our Alice and Bob key exchange mechanisms and stuff. You guys are all clear with this part, right? You guys know about all this, right? Okay. Okay, what is the quantum threat? So, as said, an integer factorization, which is our decryption mechanism for our RSA, AES, ECC, today requires a classical system, because we know we share public or private keys, or we share a secret key. But when it comes to, let's say, a quantum random number generator, do you guys know any idea about quantum random number generator? Any of you? Any of you? You have? Okay. So What is a random number when it comes to cryptography? What is a random number? Why do we generate a random number, and how large is the random number? So let's say like this. There is a random number generator called QRNG, which is a quantum random number generator, where the generated number, the quantum random number generated, is shared via special protocols, as someone asked previously about BB84. Someone did ask, right? Yeah. So these are new protocols that are being designed to secure our communications of future. These might not be the concepts that we will be using today, but these are the standards that will be mandated for the world of tomorrow. Okay. Okay. Entering the idea of quantum physics. So, as we all scientists go by, with the famous quote Arindam Ghosh sir again started with, by Richard Feynman, if you guys think you understood how quantum mechanics actually works, that means you have not listened to the presentation, or you have not understood the overview of what the subject is. Quantum mechanics is a mystery even to the highest research scholars, to the most qualified technicians in lab, because you assume it works like that. You can never define it works exactly like that. That is what the whole of our ecosystem is running behind. So let's say the three principles that quantum communication and quantum cryptography relies on is superposition, measurement, and no cloning theorem. I'll go from bottom. What is no cloning theorem? A no cloning theorem is information here in quantum ecosystem or any communication is primarily on this topic, that an information or an energy state of a photon cannot be copied into another. Yeah, before that I also wanted to tell you guys one more important thing. How many of you guys think quantum computer is a storage system? How many of you think quantum computer is a storage system? None of you. Beautiful. Why? Why? Any idea why? Anyone can go. Louder please, anyone? No. Why can't we store data? Yes, beautiful, beautiful. So this is a very important topic, that important point you all should keep in mind. Okay, classical systems are storage system. We will never ever replace a classical computer with a quantum computer. Be very clear there. Okay, every data that is migrating, every storage, every computation that we guys are doing is going to be stored in a classical system. A quantum computer is not a replacement for a classical system, but a quantum computer is a replacement for processors. It processes information, it processes data very efficiently, and we use quantum computers and quantum systems as processing units, which has its own way of processing, which is way efficient, but again, not for all. Similarly, no cloning theorem comes into picture here. Okay, our bits, we can copy our bits, we can store our bits, and we can save it for a very long period of time. When it comes to quantum states and quantum measurements, you cannot copy the information of a single photon and store it. That is exactly what the no cloning theorem comes into picture, because if it cannot be copied, then how can you use it? Okay. Similarly, measuring disturbs the system. What exactly is quantum measurement? What exactly is quantum measurement? So, just like our classical measurements, we measure what is the state of the transistor. It might be 0 or 1, and accordingly we save the data. But here, if there is a data encoded into the photon, into the space, and if someone tries to access it, you read what it is and you kill the system, you kill the bit, you kill the data in the bit. And what does that do? What does that do? It just says once the data is accessed, that's it. There is one single channel of communication. Okay. Then comes to superposition. Okay. why superposition is very different when it comes to, superposition is a whole new concept when compared to no cloning theorem or disturbance. Why? Can anyone tell why? Because see, in no cloning theorem and let's say observing equals changing, you are talking about encryption. You're talking about encryption. But when it comes to superposition, you're talking about decryption, because a superposition is what you will be using to factorize those large 2048 bits that I told you. So the three things are the main fundamentals of how we are going to use a quantum system. The superposition we are going to use to break the RSA keys, which will be used. Okay, I want to ask you guys this question. Why do you think we want to break an RSA system? Why do you guys think we want to break an RSA system? Anyone can answer. Why? Very plain. You can be. There's a dark answer. It's a very dark answer, actually. Exactly. You are hacking it. You are hacking it. So why, as government, as nationals, as defense, we have national interests. Do you think it is ethical to break into other federal government's information? Is it ethical? It depends on the situation, okay? But is it ethical? But here it is actually ethical, because you're protecting yourself. It's always good to run away from your enemy, but if he's trying to really attack you, it is best that you know to self-defense is always mandatory. Similarly, superposition is used for that reason, not for unethical reasons, but for that particular reason alone. Okay. Switching. What exactly is quantum communication? Just like our TLS handshake, just like all our network layers, transport layers, we all have a set of protocols that the internet follows. Every time you log in, every time you access internet, HTTPS, everything is a protocol. Designed for what? What is the difference between HTTP and HTTPS? Security. Yeah. So let's say you have two you have two options. You use a Tor browser, you use HTTP link, and you use another everyday browser, you use HTTPS. Why does your everyday browser not permit a lot of HTTP links to be accessed? Why does your regular browsers like Chrome, Safari not let you access every link without HTTPS? Because of our standards that the government has mandated. Similarly, when it comes to quantum communication, what happens here is it's not HTTP, it's not HTTPS, but a whole new type of internet protocol is being designed. There are protocols like MCEA that we are working with RRI Bangalore, where there's one phenomenon called as entanglement. What is entanglement? As Sir said, entanglement is when I am person A and I have another person B. Once we are entangled, once two qubits are entangled, no matter what the distance is between them, no matter what the connection or a communication channel is between them, be it visible optic fiber, be it an invisible vacuum space, both parties can exchange information in such a way it is faster than the speed of light. That is what Einstein, Richard Feynman, and everyone in today's quantum world is mesmerized about, at the same time have no idea why it is happening, how it is happening. Okay, so we will be using quantum entanglement to share information. And if there is an interception, or if there is an intruder in the middle of a communication, if there is an intruder who tries to access it, what happens? What happens in a classical? Yes, sorry, sir. It disturbs, exactly. Why does it disturb? Why does it get disturbed? It is again said by Anindam Ghosh, sir, because quantum states, quantum phenomena, qubits are very, 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 very susceptible to temperature changes. That is why we use superconducting cryogenic chambers. Superconducting, let's say, as said, there are multiple architectures for quantum computers. This is not just our semiconductor technology of classical systems that we use today. But every system architecture like superconducting, trapped ions, neutral atoms, photonics, everything has its own set of rules and its own separate architecture where not every code, not every algorithm that you write works on every other architecture. It's like a Java code or a C code cannot be run on a Unicode platform, right? That is why we bought in Java. That is why we bought in Java, because it's Unicode. It is platform independent. But when it comes to C or shell script, it was platform dependent. Was it? Was it? Okay. Okay. So let's say platform independency. Do you guys think platform independency should be mandated for quantum computers? Platform independency. That means, suppose you write an algorithm for a superconducting architecture. Suppose you write an algorithm for a superconducting architecture. Should it run on a neutral atom system? But it doesn't. But it doesn't. That is why there is a new approach by Google. It's called quantum ecos. It is a factorizing algorithm where the algorithm actually simulated. It is not physically possible, but it simulated breaking of an encryption key, which would take a classical supercomputer 13 billion years, a Willow chip with 64 qubits, and a Willow chip with 105 qubits, did it in 4 minutes. Did it in 4 minutes. A classical computation that would take 13 billion years can be broken in just 4 minutes with 64 to 105 qubits. So if that is the case, imagine the amount of data leak that will happen around the world. Imagine the amount of information or the security protocols that will be broken in just matter of days, and the whole of internet becomes very vulnerable. Okay, so again, to come back to polarization, information is stored like once you encode an information, you polarize a photon, and accordingly information is stored. And the reason why it is very effective is because it is not just ones and zeros, but it can have infinite number of values according to the phase that you encode it into. Phase again and the spin of the qubit, it all comes together. That is again math heavy. I don't want it to be math heavy here because not every one of you is into the system. If I go math heavy, I know everyone is sleeping and even I will be like, okay, not the right time. I just want it to be as easily understandable as possible, and that is why I'm not keeping it math heavy. If you guys want it to be more detailed, you guys can let me know, stop me anytime and ask me. Okay. Okay, quantum cryptography. Okay, so sharing keys is cryptography. You have to share keys with two vendors, you will have to communicate, and all that is happening. What happens here is, let's say there is this protocol called as BB84 protocol. Okay, what is this BB84 protocol? What is QKD? QKD is abbreviated as quantum key distribution. Beautiful. Okay, how different is it from our AES? How different is it from our RSA? In BB84 protocol, there is Alice, there is Bob, we exchange keys, but the most underlying concept is no cloning theorem and superposition here, where when you try to measure, when there is an intruder between the channel, what happens? When there is an intruder between the channel, what happens? The state changes, but not every time there is a big change of state. Not every time there is a big change of state. But there is something called as, what is that? Okay, there is something called as noise. There is noise introduced into the system. Sorry? Yeah. So, when there is noise introduced into the system, what happens? At the end of the communication, okay, in BB84 again, you have two bases. One is diagonal basis and one is rectilinear basis. So what happens here is Alice and Bob, they share their information, they exchange keys, and what happens, they measure it in both the bases. In the wrong base, if they try to access the information from the wrong base, they get a wrong value. But when they access it from the right base in which it is encoded, they get a right value. So what happens here is, if there is an intruder, the base change also gets affected, and the data or the end transaction or the end result is affected. How is it affected? It is not fully affected, it is not zero affected. It is partially affected. And how do you calculate this partiality? Is when you set threshold as per the noise correction of your system, noise correction of your architecture. So let's say there is a threshold limit of 10 to 11%. If there is a threshold, or if there is a noise or a error shift of more than 11%, you say the system is being intercepted, and this is not going to be a safe channel. But if the system doesn't have error less than the threshold, you can communicate. You can easily approve the communication channel. At the same time, how does this affect, how does this approve, is when we come here. Classical cryptography and quantum cryptography. You guys know, you guys can look at the table and you guys can figure out. So math-based security, physics-based security. We talked about this the whole time. Math-based security, you have a quantum computer large enough, you can break the key in matter of minutes. But when it comes to physics-based security, physics is the underlying phenomena that just guides the whole of quantum, from sensing to cryptography to communication to material synthesis, everything. You can't mess with physics here. You can always alter math, you can always project, you can always derive. But when it comes to physics, you are not controlling the qubit, you are just channeling it to perform it that way, and you are just going to trust it, saying, yes, this is one channel that I'm going to trust and I have designed it. You figure out the result, you get the approval only at the end result, not in the middle. That is exactly why quantum cryptography is very secure. Again, when there is a intrusion or interception in classical, you cannot trace it, you just can't trace it, you have no idea where the intruder was from, you have no idea how many intruders came into the picture, nothing. But when it comes to quantum cryptography, it is very simple. Just with the amount of noise in the system, just with the amount of, let's say, error rate that you have encountered, you will clearly know at what point the amplitude shift happened, at what point the photon phase shifting started, and at what point you lost the signal, and at what point the qubit collapsed. Yeah. It is, okay. It depends on the system's architecture on which you are building and polarizing the photons. So let's say like this. If in BB84, let's say, okay, this is completely running on classical system. BB84 is a classical approach to quantum cryptography. You guys are clear? Any doubt there? It's not a quantum channel. See, I'll tell you. Okay. Think like this. QKD is where you're generating the key and you're distributing it. BB84 protocol runs on a classical system. Okay. I want you to be clear here. See, what happens here is, in QKD, you're generating a secret key. You're exchanging the secret key. But when it comes to saving those secret keys, you're saving it in physics. Okay, you're saving it in qubits. But where are you saving it? Who is the one who is verifying it? Classical. Classical is the underlying. When it comes to PQC, the whole entirety of PQC, it is a classical computer that is performing all this. It's a post-quantum cryptography. Yeah, I'll get that, I'll get there. The thing that I'm trying to cover here is QKD works on, it doesn't run on your quantum computer as such, but it runs on quantum simulator that is built over our classical systems only. Till today it is the case. Because polarization happens, key generation happens over classical, over quantum channels. But to exchange and to say, let's say to exchange and to verify it, you need a quantum channel. That is exactly what I'm, how do I get, like, do you have, okay, I'll go with math here, okay. Okay. Okay, sorry? Yeah. 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 Okay. Ciphertext again, that is what I'm telling. It is what you're going to verify at the end of the day. It is what you're going to verify at the end of the day, right? Saying, this is what is here, this is what I've got. If I'm not getting this, I cannot verify that. So, where are you storing that ciphertext? Of course, that exactly is what I'm trying to say. QKD works on the mechanics of quantum physics, everything, but the communication of all that happens over a classical channel. Yeah. Yeah, exactly. Okay. So, let's say for today, there are two mechanisms that we are primarily using, not just two. One is an optical fiber, and another is satellite communication. So what is the medium of satellite communication? Yeah. So it is radio waves. Yeah. So you are communicating using what protocols today? Yeah, BB84. All of that is running on a quantum hardware or on a classical hardware? Classical. That is what I'm getting at. It runs on, okay, to clear your doubt. Yeah, I just want to, sure. Okay, so, yes, exactly. Yeah. Okay, so BB84 runs entirely on quantum physics, quantum phenomena, it is simulated as of today, it is simulated on a classical hardware, it is simulated because QRNG devices are very, let's say it's very costly again for now. It is simulated but it is not from the quantum hardware alone, okay. But the channel that we are using is classical channel, and that is where the intrusion happens, interception happens, okay. Okay. Classical cryptography, again, future vulnerable. Why is it future vulnerable? Yes, harvest now, decrypt later. For that reason, classical cryptography is always vulnerable to quantum attacks, but when it comes to quantum cryptography, it is future proof because every quantum cryptography, that is PQC that we are doing, is going to be made, or it is going to be constructed on a classical system. For PQC, we don't need quantum computer at all. We don't need a quantum hardware for PQC. PQC is something where you toughen how a quantum computer breaks algorithms. You toughen mechanism. This is not true on its entirely what I'm going to say now, but this is what a basis is. A quantum computer is very good at solving linear equations, but a quantum computer is very bad when it comes to quadratic equations, okay? When it is tough for a quadratic equation to be solved by a quantum system, you, instead of just bringing in prime numbers, factoring prime numbers, you introduce quadratic equations, which the quantum hardware finds it very hard to solve. At the same time, you will have your RSA also existing on your classical systems, which offers dual layer security, okay. Similarly, you are breakable with enough power. What is enough power here? more number of qubits, more number of logical qubits. If you want to break a quantum PQC, you need to break the laws of nature, which is not possible as of today. Okay. Again, what the world is doing. Okay. The reason why this is important is because we are all here with not complete knowledge of quantum. We are not here who are physicists, or we are not here, trying to go in depth. But we are all here because there is something happening in the space of quantum. There is something happening so wide that everyone knows that quantum is going to touch almost every industry in tomorrow's world. And we all want to know what is going to happen, and we all want to know what can we do in order to secure a space? What can we do to do something for the country, or maybe for the quantum space? So that is exactly why this slide exists. People doing great things in around the globe is, China has this MISCUS satellite. How many of you have heard about it? It's a MISCUS satellite. They're using quantum channels there. It's again and again and again. Most of the things that we see or see on papers is theoretical. The maximum that satellite communication that they were able to do was 300 miles. 300 miles. More than that, they have tried, but they have an error ratio of more than 40%. They cannot just pull it off like that. They cannot pull it off like that because the information that is being transmitted is lost. There's no point. For that, in India, in IISc, they are doing it using optic channels. They did it very successfully with an error rate of 7%. But their channel was, optic fibers. Beautiful. So their channel was optic fiber. So when there is a channel or when there is a medium, it is easier for us to understand how it works. It's easier for us to understand where the intersection happens, how can I avoid that. But when there is an unknown channel, when there is a large distance or gap, we are still finding it difficult because we are not able to optimize the quantum systems, because we don't have the engineer or the human resources rich enough. We have human resources. We have people who are enthusiastic. We have people who want to explore, but we don't have an ecosystem, or it's been almost like 3-4 years that I've explored this space in and around a lot of domains. We are all enthusiasts. We are not experts, not on quantum computing I'm talking about, but on classical computing. That is why I always say to any audience that I address, if you want to explore quantum, in any domain, make sure you are a subject expert of that domain in classical system. Without the subject expertise in that particular domain, you cannot approach it in quantum way. You cannot approach it using quantum computer, because quantum computing needs something called as in-depth knowledge on the subject. Only if you have that, only if you know how the basics of how things work in classical system, you can approach it using quantum simulators or any other solution. Okay, and what are the other things? USA again, quantum internet. So what do you guys think will be the quantum internet? What is quantum internet going to be? Any idea? Let's say there is hacking today. There is a lot of, let's say Trojan. Trojan is a virus that literally leaked billions of, it literally broke millions of companies. They went bankrupt just with let's say 2 minute notice, the whole $3 billion was wiped out of market. Why? Because there was one virus called Trojan which literally broke and leaked billions of data. But quantum internet enables something called as new set of protocols for the world. New set. For that we need audience like you. For that we need engineers like you to contribute. For that there are ecosystems in IBM. If any of you guys are interested in contributing to Qiskit ecosystem, it is available in 2 languages again. It's in C++, which is the latest version, and it's also available in Python. If you guys want, the IBM quantum community is very open to enable or give access to contributors to their repo, because out of almost 31 repositories from IBM, India has access to just one repository to contribute. Why? Do you guys know why we say we are, as Indians, we are doing this, we are doing that, the government is providing support, everything is happening, but the whole world is still treating Indians as the second tier of civilization, even till today. You go and ask China, you go and check out USA, they don't treat India as competitors at all. And that's a very concerning space, because of the amount of engineer ratios that we produce today is it's very, very close. It's let's say it's 0.9 to 1 ratio. But the amount we saw, right? We have 91,000 engineers getting out, but Europe has almost 1 lakh students coming out. But the patent or research or publication that is happening, you guys saw that ratio, right? How different is it? Why aren't we pursuing it? Why aren't we? Any idea why? Because the main reason is because we don't want to explore. Simply, I go to any college, any student, and I ask them, do you want to write a paper together? Do you want to explore? He's like, sir, can I get a job? Sir, can I get a job? Of course you will get a job. Only if you are stubborn enough to say, I want this, I want to explore this field, and it is tough. Math again is taught as a subject where you just have to get passing marks and just go out of college. But that is not, if you don't understand math, you are not going to solve any of your quantum Fourier transforms here. For understanding each and every single gate, you need to understand how math works, how to apply math. Okay, so for that reason, Indian government is again sponsoring, they're supporting you with lots of access. Workshops like these, the Karnataka government is upfront building, let's say, they're building Q-City. Q-City is Karnataka's most ambitious project for the next decade, where, let's say, we all use Google Cloud Services, AWS Cloud Services, but is there something homegrown from here in India? We call it Zoho, but it's not homegrown because it originated elsewhere. So similarly, the amount of support that we guys are getting from National Quantum Missions, Karnataka Quantum Mission, Q-City, tomorrow's Cupa AI lab exploration, all that is just opportunities for you not to just witness and just fade away, but we want you guys to be an active participant here. Okay, that said, yeah, these are some places how the world will change when it comes to quantum. Defense networks. Again, as said, PQC, communication, defense. That is like the most, yes ma'am. Yes ma'am. I am the only Indian in my company. My core 7 members in the company, we are scattered around the globe. We are all MIT X-Pro students, where we started our research there. And then the whole of my team resides in Denver under the professor of John Karsinski. He is the guide, and we have established a company. We have 7 core members. We have 43 interns now. We are all, no, we have Indians also. We are actually picking up, we are conducting hackathons, people and students and teams with good amount of exposure or good learnability. We are bringing them into the organization, training them with our projects, helping them explore what they can do in that space. And as it is a startup ecosystem and we are completely bootstrapped, we are keeping it very small for now. But given the funding and opportunities that we are receiving, we are actually in plans of signing deals here at KSTA. We are setting up COAs in colleges in India so that people get exposure to quantum technologies. Because every resource today, I see second year graduates from Europe, second year engineering students from MIT, setting up their quantum communities, setting up writing research papers. But if I go to an engineering college, if I am invited to my own engineering college and asked to deliver a speech, and I give out a speech, what happens is they are ready to listen, they listen, they get inspired for the session, during the session, walk out with no ambition. Why? They are not ready to invest time. That is a very tough part. I don't know how to convince students or faculties or institutions to say that students, this is not just going to be your hustle for marks, this is not going to be your hustle for, let's say, just to get a decent job and make money for life. This is going to be your hustle for the nation. You guys should be ready to invest time. This is not going to be your 9 to 5 at all. If you are focused on 9 to 5, this is not a domain for you, because we are exploring and we need engineers who can explore and give their whole time to this ecosystem. So yes, ma'am, to answer that question, the core members of my company are all from Denver. They're all from Denver. They're all my peers. And my interns also, out of the 43 interns, I don't know if I have to use the word ashamed, but I have tried to recruit a lot of Indian students, but for now I have 4 Indian interns, just 4. Can you be more clear, ma'am? Yeah. Okay. There are multiple roles. Firstly is research. Research is again math heavy. Research is again time heavy. People who want to do that, they are welcome. They are always welcome. But given they are an expert in the field, a startup never hires a mediocre student. A startup never hires a mediocre student because we are limited with resources. We cannot pay a mediocre student. But if you are really brilliant, if you are really, really enthusiastic, we will love to spend money on you. So that space is what we are looking at. Because as said, ma'am, BSc Physics, MSc Physics is not the idea at all. Even if you are a second year student with complete, or let's say with very good strong fundamentals, you are welcome to work in our organization. Okay. No, ma'am. So it's not just going to be a degree that matters in the quantum space, because let's say like this, ma'am. Today's code that you say is Python, whatever code. Okay, how many of you are IT engineers? Any idea? Have an expertise? Okay, IT engineer. How many of you code? Or majority. How many of you use ChatGPT or LLMs to code today? Most of you. Okay. So is writing a very advanced algorithm tough today? Is it? Even if you can just imagine the algorithm, you can still feed and generate code. Right, ma'am? Writing algorithm, coding. Yeah, you can generate codes. You can easily generate code. But let's say, is that enough to be called a smart person today? Is that enough? If you know how to use the LLM efficiently, is that enough? I would take example of Sir Arindam Ghosh again. When I was talking to him about quantum sensing, he told me this: Darshan, we are building a device where we're trying to sense the mineral rich soil in the agricultural lands using quantum sensors. For that, they didn't do much. They didn't go dive deep into it, nothing. They just announced it as an open challenge to their students from IISc. Out of 100, let's say there is an 100 pitch, there was only 2 students who wanted to read research articles and then pursue the mechanics, and then pursue how to do it. Rest all, they just told a problem statement to an LLM, generated an approach, and when questioned how does it work, they don't know the underlying concepts. So that is very tough, right? That kind of human resource is tough to handle, right, ma'am, in a startup environment. So that is, again, that answers your question, ma'am. So we love to hire lots of engineers, but we just are very cautious about hiring a very qualified engineer, that's it. So yes, short term, okay, yeah, midterm financial networks. Market predictions, companies like HSBC, companies like Vanguard, companies like BlackRock, or McKinsey & Co., they are all using quantum Monte Carlo simulations to optimize their portfolios. Why? Why do you think is, yeah, I'll have to touch this topic, machine learning and quantum, because how efficient do you think will machine learning turn into in future without quantum and with quantum? Okay. How much energy do you think is required to generate a image over an LLM today? How much energy? Any guesses? Let's say 100 watt. Let's just say 100 watt. But using a quantum approach, using quantum optimization, the amount of energy that will be required will be brought down by 99%. At the same time, the time efficiency will be increased by 1,000 times, because quantum computers are good at handling large data, but they are not good for small computations or small scale data. Quantum computers are built for large set of data handling because they have this phenomenon called a superposition, which enables them to be in multiple states, and it also enables them to, any idea? Compute differentially. It computes in a very different manner. I have a YouTube video or something. You guys have seen about, okay, not this. There's a YouTube video that shows very clearly of how quantum actually solves. I'll try to find it here. So internet is working, right, sir? I have it in another presentation. Do you have a C to HDMI, sir? Okay, I'll find the video and I'll share it with you guys sometime. Okay. Okay, final takeaways. Okay, classical security is temporary because, again, as said, you can harvest the data, harvest critical data today, and you can always break it tomorrow using quantum computers, and that is not a very safe place to be when it comes to the exponential growth of the quantum ecosystem and quantum computers that we are seeing today. Similarly, for quantum cryptography, you will be mandated by the year 2030. Every internet protocol, every TLS handshake, every HTTP, HTTPS will be let's say, will be replaced, not completely replaced, but will be guided using PQC standards, will be mandated to follow PQC standards. Yes, from just trusting, you are not just going to be trusting here, but you will be verifying it every second, every minute, Because quantum cryptography and quantum algorithm says if there is an interception, if there is an intrusion, we will get you notified that there is one intrusion. Similarly, we want you guys to contribute in strategic and national interests. We want you to invest time. We want you to, invest more time, explore. Maybe you like to deal with finances. Use quantum there. Maybe you like to deal with cryptography. Use quantum there. Contribute to the system. Make India more, prowess in this world, in this ecosystem. And career defining, as ma'am wanted to address. You're all welcome to work in organizations, and there are multiple organizations, multiple startups here in India, privately funded, government funded, bootstrapped, and everything. But go to any organization, go to any junior resource, I'm pretty sure he practically knows a lot more than 100 mediocre students put together. And he can do a lot more than 100 students using LLMs. That is what defines why he is hired in the quantum ecosystem and these 100 are not. And that's it. If you have questions, please. Thank you. Okay. Okay. So, let's say this. We are building something called as NCEA. Okay. I can't talk much, but I'll give you a brief picture. Okay. It's abbreviated as multi-channel entanglement-based authentication system. What we're trying to do is we are integrating it with a concept called as QSF, which is quantum security function, where this quantum security function acts as the interception reader. If there is an interception in the system, we detect it, because detection is very mandatory here. We just say till now we were talking just about if there is an interception, we get to know. Who is going to find it out? We never talked. That is what we are doing in QSF. And then when it comes to MCEA, we are doing something called as multi-channel entanglement-based authentication. For this again, like your QKD, we will need quantum hardware. We will need QRNG devices to generate a random number, using which we will be entangling two qubits. Using those 2 qubits, we are trying to authenticate multi-channel. I'll say like this. Let's say this is a qubit, and this is another qubit. These two are entangled. That means they share a key. And this only if these two are approved, you can establish a secure communication. No, this is completely device dependent, because a quantum hardware has said you need 2 quantum hardwares here. You need 2 quantum hardwares here because you are handling 2 qubits. You are measuring 2 qubits. This is not going to happen device independent at all. But why are we doing it? That is because when sir talked to you about distributed computing architecture, what is distributed? Any idea? Yeah. For 2 clusters to work together, they need a handshake, right? They need a handshake. Right? We are working on that. Yes. Optic fibers, radio waves, whatever. We are going to use, let's say, if this is a distributed system, there are 2 channels. Let's say one is in USA, one is in India here. Entanglement is the most secure as of today, because for 2 systems to be integrated, we need to make sure that both are of the same architecture. You cannot have a superconducting and a neutral atom system to be distributed architecture, because architectures itself define different mechanisms. They require different algorithms. They require different, let's say, they just can't work together, 2 different architectures. Similarly, optic channels are today's only and the most feasible mechanism. looking forward to building more. That's it. Which one? Then distributed systems only. In the sense? Okay, you cannot use continuous here. You cannot use continuous here because both these systems that we are separate, or both these independent architectures, they will work on their own specific set of bits, qubits, and these systems cannot travel, but there's just one communication channel where there's no data transfer, there's just security transfer, because every job as of today is independently computed on different architectures, different systems, because you cannot transfer data because the data gets crashed very easily due to the noise.
No, madam, we can interact with during lunch time, so we are running out of time. So anyway, it's an excellent lecture by Darshan sir, and is really inspiration to the youngsters. It is very difficult to get a PhD in MIT. So any one of you, please, your students, maybe you can also contact Darshan for further communication, for any suggestions or internship for your students, or any quantum cryptography related aspects. You can mail us, or you can directly contact Darshan. Is here. Maybe he will traveling maybe next month to USA. So we will assist her with Darshan. So please, once again, please give him a big round of applause. And we will have a quick lunch break for 30-40 minutes. Please come back around 2:30. We'll start. Next lecture is already here. So thank you. Please assemble back at 2:30.
You can share that link to us. So we'll share.
Sure.
Nicely
live streaming.
explained.
Was the first time looking at there is something different from the way we understand nature, right? So Newtonian physics explained a lot of things, and around 1900s Planck's quantum theory came. I mean Planck's idea of is radiation theory, and then there was discovery of light as as quanta, and many things happened. But almost for 80 years or 83 years, there are a lot of debates, discussions, corrections, improvisation, just to understand what is the way that nature is designed for us. Right? So it's only after 1980s people started controlling them at the experimental level. Like you could actually go to lab and then try to establish or understand what was constructed as a theoretical foundation. So only after 1980s and around 2010, it was not just understanding. You can start. People could control atoms, bring them together, move them apart, or people could actually see or like detect photons, control electrons with magnetic fields. So a lot of things started happening in 2010. So that's where he said, okay, it's not just about understanding nature, now we can engineer them. The moment we can start engineering some of the things at fundamental level, either it's atoms or photons, then there will be a lot of scope for technology development. Then that's how we see next 20 to 30 years. We like it or not, it's nature's gift, right? Nature is telling that there is so much of hidden treasure in me, so you can exploit for your resources. That's an invitation from nature. That's how I see quantum theories. To give a good analogy for that, you all might, if I just ask you, which was the biggest discoveries of mankind? Let's go back to our prehistoric era. Huh? Fire and wheel, right? I think these two things comes as, and that ruled for hundreds of years. Improvisations, and even today we can't live with it. After that, if you say, what is the next level which came? Electricity, okay.
before that, yes, electricity is one, electricity came, but there is something else. Hmm? Fuels, yes, okay, related to that. No, fuel, steam, right? Steam is, see, I mean, the most simple thing. Fire, if you say what I said here, if you say 1900s, we said there was something which we tried to understand, we could not control them, and only in 1980s we started controlling. Fire also, it was the same thing, right? Prehistoric era, if you think they saw somewhere fire and it only destroyed. When people started learning to control fire, they started seeing it as a resource. It's the same with wheels, right? It could be some rolling stone which has probably, somewhere, some habitat, or like somebody was killed or something happened. But then if you can shape it, if you can control it, then it's under your control. So that's how the revolutions keep happening. So steam, it's a simple thing. I mean, there's a frame and then there is some steam and it's giving some momentum. Now that gave birth to whole of thermodynamics and then steam engine, the precision engines. Even today, we are mastering it. And then comes an electromagnetic theory, right? Electricity, magnetism, they all came independently, but then if you look at them as a theory, electromagnetic theory explained. And even today we are relying on that technology, right? We are talking about new technologies coming, new revenue, just that exploiting our electromagnetic wave spectrum in some different ways. There's nothing more than that. There's a big EM spectrum and they all have different wavelengths and you can tap them in various different ways. You talked about mobile phones, you talk about remote controls, you talk about everything. They are all EM theory, right? Now that is again something which has come from nature. Now these are, we are not inventing something there, which is not there as a contribution from nature. It's nature's gift. So now the same thing, what happened was you started looking what is happening at atomic level. How is the nature defining atoms together? How are they bounded together? How are things happening at the most elementary level? So now that is again a theory which came in, and then over like last few years we have started controlling. And that's how the economy or how the countries or everybody are looking at this is a resource. How do we learn and tap them? So we might be talking about communication, we might be talking about computing, we might be talking about we researchers talking about quantum sensors or many things, but that's still a limited scope, I would say. There can be many new things which can come in. All that one needs is to understand things at the elementary level and then see how now you can use them as a resource and how do we start controlling them to develop technology which can serve or help mankind, right? So this is just a beginning. That's how we see. It's a beginning of use of quantum resources to build technology. So it's science, engineering, everything together, right? As I was introduced, I did my physics, and even today I only identify myself as a physicist, but now I'm also part of engineering department where you build engineering system. I don't have any engineering degree, but the science are becoming, science or technology is becoming borderless. You just have to navigate through the resources and start understanding and building them. So there are there are people who have, there are a lot of research which claim that quantum computers are there which can do better than anything which classical computers do. I'm not going into details of any of them, but I just give you some idea of what kind of work we do in our lab related to, like in our research group related to quantum technology. So our group is quantum optics and quantum information. So one of the most important thing for any of us is to just understand nature. That is the most fundamental thing. Only when we understand we can start engineering from that knowledge. So we develop or we look at quantum algorithms which tries to simulate some strange behaviors in nature, which means that we are trying to model them and understand how certain things happen in nature. We already have many things, we know many things, but then there are many things like photosynthesis and various other minute dynamics which happens at the atomic level which we don't understand. Can quantum algorithms and quantum computing help in that? So we look at it, and as a big challenge for us under even National Quantum Mission or for our initiative is to build a real quantum computer in India. So our lab works on photonic quantum computing. We build quantum computers using photons, and then communication is also very important topic. I'll just give you I'm just giving you a big picture so that when I start explaining a bit of detailed quantum mechanics in the framework which we study. When I say quantum computing, there are many things which come, communication, there are many things which comes into the picture. But keeping all that aside, I'll give you a simple example which we all use on a daily life. I think, was there any mention about quantum random number generators in the previous talk? No, right? Okay. You all get your OTPs, right? I think nobody is these days spared. And this all started only a few years back. So where do we get your OTPs from? Sorry? From some server, right? You get your OTPs from server. How does server generate OTP? Random numbers. Okay. How does random numbers come from? Sorry? Some kind of algorithm, right? So who writes algorithm? Human writes algorithm, right? So now, if I am a national security, or like I'm looking at something very sensitive information, and I need certain OTPs. Now I should ask somebody to write algorithm. Now we can write an algorithm which looks random to you, and it can be hacked, right? This is a very serious concern, and there is no algorithm which can give you a pure random numbers, because every algorithm you have to write a code, which means you are writing a methodology for it to generate. It means that you can reverse engineer them. If you know the methodology, you can know what the numbers sequence will be. So this is a very serious threat for high level security. It doesn't matter to me or like all of in this room, I believe none of them would be multi-billionaires here who would be worried about it, right? We all would keep a small fraction of money in that perspective. So OTPs really doesn't matter, but for various serious concerns, OTPs matters a lot. Now, where can quantum mechanics help here? So I think this explains the whole purpose of why we look at quantum technology. Like I don't actually have to go to many of my slides here. That will only make you sound a bit more mathematical and then in a framework. Now, nature itself gives you some randomness. If you rely on nature, I said, no, you don't write code. Nobody will want to trust anybody. So I don't ask anybody to write code. I will say, nature, you give me random numbers. And we will use that for security. So nature can actually give us a very genuine random numbers, and that comes from quantum mechanical systems. So I can take atoms, or I can take photons, or I can take any spins. You might have, many of you are from physics background, you said, right? Electrons are spin up, spin down or something. And then you can choose them as your degree of freedom. Photons polarization, horizontal, vertical polarization. And now whether the photon is H polarized or V polarized, you can make it 0 or 1. And then that will give you, now that comes to a measurement of one part of my talk, why quantum mechanics gives you randomness, a natural randomness. So now that becomes a very big resource, right? So there is one device which we had built in our lab, which is a random number generator. Similarly, we have photons inside. They collapse to one of the either polarizations, then it gives a bit string, zeros and ones, and these are currently being used, some of our national agencies, for their random number generation. I was just talking to somebody in defense when I said, this is a bigger version. In future we might want to make it compact. He said, no, in defense we would like a big versions, right? Because they can trust something, how this is happening. There is something physical. If you just give them as a chip, somebody could have written some malicious code at the backside of a chip, and then defense people don't want to trust such kind of thing. So this is just an example, one of the simple examples to see how random numbers can play a role. Right? Like right now we get our OTPs. Now there are certain agencies in India and abroad where they try to get their codes from a quantum mechanical devices so that they are naturally random, defined by the nature, right? So what? Bit size, there are many ways. This gives about 60 to 50 to 80 million bits you can get. That's a lot of bits if you want to generate. So it can give about 70 million bits. So that's only one simple example. Like there's one more. You go to your bank, you give one number, you enter your code, and how will bank believe that it is you? It will have some other number associated with your number there, right? And then it tries to see a match. Now this also mathematically is a factoring problem, right? You have two different big numbers, and if you put them together, it has to give you one particular answer. Only then they trust it is you. So, but what it's mathematically in mathematical terminology, cryptography, what they call RSA cryptography, where you can have a very large number, and then if you have them finding factors for them is very difficult. So now we believe that you can use them for cryptography. But what is established is that if you are given a very powerful computer, you can crack them. so mathematical hardness can be cracked. So that's where one thinks that if you use a natural quantum mechanical system to build not just random numbers, can we come up with some keys which are defined by nature and not by some mathematical complexity. So because most of us trust nature more than our own invention of mathematical complexities of a few things. So there are applications like that in quantum communications, and quantum physics plays a very important role. So there are other versions which people are trying to look at, sensing, and there can be some landmines, and there can be some iron or mineral detections or anything, right? How do we test whether there is some mineral there or not, right? People use some sensors. So sensors will detect some deviations from your regular pattern by certain efficiency. But if you can use an atomic level devices or something which are built out of atoms or something, they can be much more sensitive. So these are the areas which people generally work also, and this is also the focus of our research interest. We do work on all of these problems in our group. Okay, so now let's say, now this is a bit elementary, how we go, what are the basic. So I think this, most of you are familiar, right? The photoelectric effect, and there was hundreds of years debate even before that. There was corpuscular theory, then there was again wave theory of light, because corpuscular theory was not considered as probably a right model, and then there was wave theory, and then Einstein's explanation came for the photoelectric effect, which said that you might have a light of a lot of some particular energy levels, and then if you are hitting it on a metal, only above certain energy level you will end up getting electrons ejected out of it, and then they are in multiple steps. So we call them as quanta. It means that the photon itself should be like balls, like billiards or whatever we talk about. Only if you are hitting them above certain energy you are getting back. So then it said, okay, light does behave like a particle. But then the question still remained a very confusing one, though Einstein was given Nobel Prize for this later on. But there were other experiments to give an analysis for that. You can have, or called thought experiments. So when you are again have an atom or something and you are sending some radiation, the emission will be of only some particular wavelengths, and you don't get emission of different wavelengths, mainly because there is an energy levels. Electron will sit in one energy level, it goes to an higher energy level. When it is coming back, or if it's coming from N3 to N2, then it is emitting an energy of only particular wavelength. It does not emit any energy which is half of this, somewhere in between here, right? So which means that electrons are sitting in an orbit kind of thing, and they are not anywhere where we are looking at. So that kind of gave that there is a discrete nature in the way we see subatomic level dynamics. Okay. So the idea that the light exists as a tiny packet or particle that we now call as photons. So alongside with Planck's quantum theory of light, Niels Bohr's work, all of them together started building as a building block for quantum description of nature. And this again, they all remained as questions, but they were evidences for them to explore more than that. It was only till it took some other 20 years. It was in 1925 and 1926. There's two important papers which came, and that's why last year was celebrated as International Year of Quantum Science and Technology. It's because there are these two papers which kind of created a proper framework of understanding such kind of behavior, of quantum behavior of light hitting particle metal and then getting something like. So whole description happened, and then there was a theory to understand atoms and molecules together. So that's why we celebrated 100 years of quantum theory last year. So it took many years from here, I think 1905 till 25, to debate and argue and come up with the Planck's theory, quantum theory. Now I'll give a very simple example. This is not probably everybody looks at it. I want to see this in two different two different framework. Double slit experiment, we all know, classical optics we do. When I have one slit and other slit closed, if I send a light or electron, it can be light or electron, it doesn't matter, right? If I'm just sending, I end up having them all accumulated in a string, and I get a proper distribution of them on a screen, something like this. So naturally, there are what we should expect, that if it is some pattern like this, if I have two similar kind of slits, then I should end up having something like this, right? So that's what it says, a particle nature. So we said light is like a quantum, and then you have a discrete gems, which means that photons are coming in packet. If they are particles, then we should end up having something like this. But what happens in nature or naturally is different. Okay. So what we end up seeing is not A, but we end up seeing is B. If I have only one slit, then I will end up seeing this. But if I have two slits, instead of seeing something like this is what our natural thought should be, but we end up seeing some interferences happening. Then why should it be? Now, it's not just particle. That's what they started thinking about it. No, it should be both wave and particle together. So if you are saying which path it is going, then there should be a particle behavior. If you're not seeing, or if you don't have an idea, then there would have an interference, and you end up seeing it as a wave. And that's something which, wave particle theory or wave particle nature started coming into a debate and argument over within the community. So what do we get? So that's what I said. When we track a photon, whether it's going to one particular path, this or this, then I would end up having something like this. It means that I should follow where the photon is going. If I know whether photon is going here, then I will end up seeing here only. If I know photon is going here, I will end up seeing here only. But if I don't see, then I would end up having, it's a strange thing, like why should me seeing it or not seeing it matter a lot? That's a big question, but the seeing should be seen slightly more differently, which means that you are observing here as something called as a collapsing of wave packet, measuring, which means that you are identifying. When you talk about uncertainty behavior, it has a wave packet kind of nature. That's what we call, right? So when we say wave packet, now wave and particle nature are together. There is some uncertainty associated with where the particle is. But the moment I'm trying to see, I have identified that fraction of second there. That's all. If I'm not observing, then there could be a wave behavior there again. So that's something. Now there are other experiments which kind of amplifies this in a much more bigger picture. I'll give another simple example here. Now that could also be a reason that the photon is splitting into two photons, the beam splitter, and you might end up having an interference. It's a particle splitting also was one of the arguments which some people came up with. But then there are other experiments you talk about. It's a beam splitter, right? I think it's a very simple way you can talk about a mirror of 50-50 transmission and other is reflection. So we simply call them as, if I'm sending a light, it splits into two, classical light. This light, if I'm sending it to beam splitter or something, I would end up having 50-50 intensity at both the points. That's how it behaves. So what should happen if I send a single photon? It should be like, if I'm sending single photon, like 10,000 or hundreds of photons or something like that, then 50% of them should go here, 50% will go there, right? So that's how it should happen. If I'm just sending a single photon, it does not, right? So, yeah. So now what it happens, that experiment says that if I'm sending single photon, I will only see a detection here or here. I'm not going to see one photon splitting into two photons. You do experiments 10,000 times, it doesn't matter. If I send hundreds of photons, then 50 will go here and then 50 will go here. But at every time, if you are looking at, there's only one detection. What we call as there is no simultaneous detection at D1 and D2. Right? So when there is no simultaneous detection, which means that it establishes photons are not splitting, they always come as a single photon. So now, when you know photon doesn't split, then there should be something more strange thing which is happening. Right? I'll just give one more example here. So we'll take, instead of having a single beam splitter, I take two beam splitters. There's one and there's one more. So now we define whether, because I said it's a single photon, it's not splitting, then it has to take this path or this path. And if I'm taking this path, I'm calling it as 1. If I'm taking this path, I'm calling it as 0. Then what should happen here? Huh? You should get? You should always, both of them, there should be some probability at both of them, right? It means that the splitting here and there's a possibility of splitting here. I should end up having, again, same thing like this, right? You all think that we should still get 50-50? No? So why? No, if no, why? And that's an interesting question, and that's the reason for me having to, I'm sending single photon, but then if I'm sending some 10, okay, one after the other. A single photon, one single photon, I agree, either it will be at D1 or D2. But now I will send 10 or 100. Then? probability? 50-50? How many of them say we will get 50-50 in both of the D1 and D2?
Cannot be 50-50. Probably maybe D1 may be very high, D2 will be less.
Why?
D2 will be very high.
Why?
Will not formally follow the direction.
No, but we are all scientists here, right? So we are all researchers. So we should be a bit more. I think you are not agreeing. So can you say no? Why? No? So let's see. Okay, I will. See now. Let's see this. If there's one photon, let's say this. We are taking one particular path, and you do go to another one, right? So there can be two possible paths here. So a photon is taking this beam splitter or the other beam splitter. That's how the way I will try to rewrite it in a simple form. So if the photon is taking one particular path, then you are calling it as stage path 0, and if it's taking another path, you call it as path 1. But what happens is you get something like this. Even if I'm sending thousands of photons, not a single photon will end up being here. Every photon will end up just taking this path. Now if you see here, if I just have one beam splitter, I'm getting a 50-50 probability here, which means at this beam splitter, I'm getting one photon here and another photon. I know it should be 50-50. Like, if I'm two, one could have gone here and the other could have gone here. But why is this strange behavior happening if I'm having both of them together? Right? So their superposition, yes. Now, what I'm trying to put things together here is that you recall the previous double slit experiment, where we said it's going in. It's not actually taking either that path or this path. It is simultaneously going in both, which means that I'm measuring here at 50-50. My wave packet, or what we call the particle wave nature is there of all of all the subatomic level, right? It is collapsing on measurement, which means even here I can't measure, but what it is saying is that even after this beam splitter, this photon is in superposition of both of them. It exists at both the path. It collapses upon detection. So it is not just going like it is not decided here itself that I'm going to take this path. It has not decided. It actually is in superposition with both of them even after the beam splitter. If it had decided here itself that I'm going to take path 0 or if I'm going to take path 1, then I would not have got this complete constructive interference to 1 and a district here. Now people can argue that no, this is not possible. Why? People did argue at that point also. When people came up with this thought experiments, people did experiments. We see that in our labs, right? We have to, when you are doing experiments, you are observing them, then now what is our role? We have to interpret what is the cause for it, because that's what we have observed. We might miss some things, that's how science evolved. So whatever we have observed, we construct it back and try to understand. So that's what we can do, both from double slit. There is no difference between double slit and this experiment. It is just a reformulating it in these two schematic here, right? Though here I am dealing with just as a particle, I didn't want it to see interference. In double slit, it's easy to say there is some interference because we all are familiar with waves. We have something which comes as a wave, we end up. Where is wave here? I can't see it as a wave, but still, what is happening is, it is not taking either this path or this path. It is in superposition here. Again, it comes here and then it ends up having a destructive interference to D1 and constructive interference to D2. Right? Now, this is experimentally people observed, and now we have to just see how we can understand it mathematically and convince that this is correct. And that actually leads to the way we do many things in our lab, right? So I will come to that. Before that, just to give a quick summary of both of them. In both this explanation, knowing which slit or a path, right? Path is in the beam splitter, slit is in the double slit. Knowing which slit or a path, it means that it's a form of measurement. The moment you are knowing where it is going, we have made a measurement. We are killing its wave nature, we are only tracking its particle behavior, right? One way to determine which path is by maintaining, I can actually define different polarization and I can define I can know this polarization is going here or not, and I can kill the interference to happen, I mean not to happen, right? So there won't be any interference. So we can, okay. So measurement collapses its wave function. So if you are not measuring, I will end up having interference, but if you have measurement, you don't have interference. Now in the double slit also it's there. When particle behavior is observed, interference fails. If information exists to link, sorry, it should be photon, it's done photon. I mean, if no information exists to link photon to specific path, the wave behavior resumes. So here I don't have information whether it's gone here or not, I'm just letting the superposition to interfere at both the points, and then I will end up having an interference pattern observed. So both these experiments are the same. When I say same means the moment I build a mathematical framework for it, it will be identical. And math will be the same for both of them. It's the experiments which are different. Okay, let's say what's happened here. When we, either it was double slit or a beam splitter, I knew I had single photons. This can be treated as, it can be a double slit or a beam splitter. I don't know what is happening there because I know what I had sent, I know what I have measured, right? That's what is in our hand when we are doing experiments. I know what is the source I have sent, I know what I am measuring, but I don't know what is happening. Now that is what we have to model. So in an example, it's like this, right? So now I'm just trying to give a small build up to the mathematics here, right? I can write them as matrices or some equations. You might, some of you have done your physics masters or PhDs in physics, you would know Schrodinger equations or anything. It can be any of those things, right? I know a source, then something is happening in a system. I need to understand what is happening. That's what we call modeling the dynamics and the process, and the measurement output. So I know both of them, and this I can model, right? So let's try to model, and for that, you know, there's people have invented complex. That's what I said. Heisenberg's and Schrodinger's work came in to make them properly, you know, fit into the framework. They have introduced complex vector space and all, but I will put it in a very simple sense, right? Now this is our system, right? So this is our system. Sorry, it's just. So we will model this system in a mathematical, and that actually helps even our how quantum computers works. That's how we are building our quantum computers, right? So this is what we had. Now I can just define, these are vectors, right? Because there is a direction associated with it. That's what we know from our +2 mathematics or 11th standard PUC mathematics or something. It's all associated with vector space. If I say for this particular 0 path, if photon is taking, I define it by a vector 1, 0. That's the direction based. And if it is in this path, is going from this way, I will define it as 0, 1. Now these are two vector spaces, a simple matrix form. Now I have to define beam splitter because that is the only component which is coming here, right? There are two beam splitters, there's nothing else in the system. Beam splitters, what it will do, it will split them into 50-50. That's all, there's nothing. Classical or like, you take classical light or quantum light, there's no difference between that. So it splits them into a 2 option. So I can, because the phase, even classical light you have phases, so classical optics also we use the same formula. I have a beam splitter. To split it into 50-50, I have to create some kind of math. It's almost like a, if you can rewrite them as a simultaneous equation which you study, right? So 50% reflection and 50% transmission. So which means that 1 and I, and if it's another state, it is another one. So it's two beam splitters, right? Now, because the phase, one which is transmitted and one is reflected will have different phases that we understand even from the classical optics. So what will happen is, a bit slow. I just multiplied. This is the state I began with. We defined something as 0, so 1, 0, and then there is a simple beam splitter operator. We actually call it a Hadamard operator. So if I do this matrix multiplication, this is 1, 1, right? This is I0, and then this is I. So I1 and I is what I will get. The 50-50 superposition is happening. So which means that this expression is defining me the state after the first beam splitter. That's all. We didn't do any complicated mathematics. It's a simple matrix of 2-dimensional multiplication, right? So now I have another beam splitter. Now I just have to take this as my input state because it is in superposition. It's not in one of the path. It is in superposition. Now if I bring in a second beam splitter and multiply, because this is what is there. This beam splitter is multiplied here. Then the output is 0 high, right? So that's what we are observing experimentally. Everything is coming to D2 and there is nothing to D1 because there is no probability, zero probability. Now I know how I can even make it not just 100%, 60, 70, 30, 40. It is just by going back to the matrix, I can bring in some different splitting ratios, I can control interference, then I can get the desired probability distribution between both of them. So that's what I said about engineering the dynamics, and that's how we build quantum computing operations. And if you are building photonic based quantum computing, that's how we control. This is equivalent to one of the famous Adamant gate or Adamant gate operations, what we call. We can control them and we can build, and that's how we start. Now this is just 1, 2 beam splitter and I'm seeing some quantum behavior and I'm getting an output. I can have hundreds of beam splitters and various other optical components, and for that, for everything, if I start writing all the mathematics, that is our quantum computer. So there's nothing much more dramatic than that. Everything is building up from this fundamental construct of what we have for a simple beam splitter setup. So this simple math shows how interference is making photon to get detected into D2, and that also helps us to show how we can control, right. So now, as I said, I had 2 beam splitter. Now I can have an array, like I can treat everything as a beam splitter. I given this example is because that is where people are scared that quantum computers, people in the sense for security or various other purposes, quantum computers can actually break their security codes because they can be very fast. It's because of this feature. What we call superposition, we said single photon can be in superposition, but it's not limited to being in superposition just only 2 places. You can have it in superposition in multiple places at the same time, because that's how we start understanding them. If I have a single qubit, it can be in superposition. This is how classical bits would look like, just 0 or 1. I have binaries, nothing else. But in quantum, I can have it in superposition of zeros and ones, which means you have an, classical, I just have an access to 2 points. In quantum, I have an access to every point on a sphere. So I can actually define every point uniquely depending on the phase. That's what we call as block sphere, and that superposition is only for 2 level. But if I have a multi-level state, then I can have an access like this. One of the famous algorithms in quantum computing, it's called Grover's algorithm, which says that, the title for that was searching for a needle in a haystack. Haystack is, so the sack, or like hay is, if you have a paddy, the remaining of that, right? Similar kind of any of them. If you have a small needle in that big sack, how are you going to search? It's a difficult problem. You put it in a simple words. So searching is a very difficult problem. What Grover said was, since quantum mechanics allows us to have a superposition, I can have a superposition of all the positions, then I will have some finite probability of finding a particle using quantum state, but it does not happen with the classical one. Like in a classical, you toss a coin. That's how our search engines work, everything, right? It randomly goes and it finds. But most of the time, they are always around the same points. It will only spread to certain amount, but it won't spread as much as the quantum wave packet spread. It's known that quantum mechanics can do a better searching than the classical systems. So this is the role of superposition. Now, in fact, this image and the previous explanations, whatever I said, it captures everything. So I will just ask one more simple question, right? I said I can engineer interference, right? So now what is the role of computers? Why do we compute? To process, but why? Yes, computer processes, but why do we use computer? To find some solutions, right? There can be a lot of solutions, or there can be a lot of options. For that, there's only one is your solution, right? Now I'll go back to our previous slides, which we were talking about interference. If you can control interference, and if you can say you should have a constructive interference for where your solutions are, and if you say this is actually capturing that. You are kind of having a constructive interference at certain points, and if your solution is something in that direction, and say, please have a constructive interference towards my solution. If you program your quantum states, then you will end up reaching your solution much more faster than a classical way. So your interference, controlling your interference is the one which is going to help you to get solutions for computers are very fast. In fact, I am actually putting things in a more simpler terms, and that's how algorithms are built. If you have to build any algorithm today, we try to look at Okay, this is a problem and this is a solution. How does a classical computer do? Can I use interference and superposition as a resource to do this faster? That's how. I mean, if I have these questions, then I can start work. It might take 6 months, 1 year, 6 years, depending on the kind of problem you're bringing, but you can develop algorithms. So that's how people are trying to use quantum mechanics. So I discussed two important resources, which you call as superposition and interference. So these do define a lot of quantum processes, but there's another, okay, I'll just give a simple how we start using them to build larger number of qubits. As I said, the single classical bit and a quantum bit, this is how we define, and the superposition we have defined. And if I have more number of qubits, I can start expanding. So this is just an example of physical systems. I said about photons, but you can also take atoms, or I can take electrons, spin up and spin down. Now depending on whether electron is in this position or this position, I can call this a 0 or 1, and if it's in superposition of both of them, it can be 0 and 1. People do control them in lab, and these are examples of having what we call qubit two-level system. So if I have two of them, I can write a mathematics like this, Hilbert space. I just took the single beam splitter, right? Now I have two photons I can build, and I can always now write them as a tensor products. That's how things becomes complicated. This is only to give you an example how we start scaling up. So if I have a 2, and the other way where all our quantum computing advantages comes in is that, so if I have 2 photons or 2 electrons, then I get 0, 0, 0, 1, 1, 0, 1, 1 possibility, which means that's 2 to the power of 2, or like, if I have 3, then it will be 2 to the power of 3, the number of possible basis states, what we call, you get. So the number of bits you will have access scales up significantly. Just to give an example of, so what is 2 to the power of 8? 256? Okay. Then what is 2 to the power of 20, 30? Do you have any idea of what would be the magnitude roughly? Some large number, right? If I have said 2, okay, let me just say 2 to the power of 50, right? 2 to the power of 50 would have 1 followed by some 16 zeros roughly. So that's the number of possible ways. So it means what I am saying is, if I have a 50 photons or 50 electrons or a 50 atoms, and if I can create them in a good superposition state, I can write like this, right? 0, 0, 0, 50 times, and all possible combinations of them. That will be 1 followed by 16 zeros. Now 1 followed by 16 zeros is a huge number, and all I used is only 50 qubits, what we call. Now that is equivalent to the best of supercomputers today. The best of supercomputers bits capacities are that 2 to the power of 2 or 10 followed by some 16 zeros, 10 to the power of 16. So that's the power which we are getting from superposition. I just gave it for, here I only wrote 2, it doesn't look dramatic, but if you just go back and then try to write for large numbers, then you would see, might be for vaguely you might have heard people are 50 qubit, 100 qubit, some supremacy, like what if you have a very good computer, quantum computer, very clean, 100 qubit quantum computer, it can do wonders compared to the classical computers, because that's the capacity which comes. That's coming from the superposition interference, and there's one very interesting feature which comes even just with 2 qubit. If I have 2 atoms or 2 photons, I can create something called as entanglement. This is again a very strange, it was called strange behavior. Einstein called it spooky action because they didn't know how to understand them. The way we communicate today is that I send some signal, it has to transfer from point A to point B. The best is 3 into 10 to the power of 8 meters per second, that's the speed of light. You can't communicate anything faster than that. But what entanglement says, which is coming in quantum system, is that you can do that instantaneously. You don't need to have a medium to transfer from point A to B. And now that happens from entanglement. So what happens is, if I take 2 particles together and I can create some state like this. What did we understand from measurement from our first single state experiment? The moment you are measuring, it is collapsing to either one of the possibilities. So that's what happens here. If I make a measurement, I can have 2 particles entangled. I can send them to 2 different locations. People have done it for hundreds of kilometers two different locations, and if I make a measurement, then it collapses to either 0, 0 or 1, 1. There are many possibilities of such kind of states, but let's say simplest one, which means if one is in one end of one end of the world, if it collapses to state 0, you would know instantaneously the other one also has got state 0. So it means that there has been some information about the other for the person who is in another remote place. So this instantaneous information exchange is enabled by entanglement. Now when you don't even have a channel to communicate, then where is the scope for anybody to hack your system? Like how can anybody even tap? Because the only issue here would be that I should create an entangled state and share. After you share, you can keep collapsing, and then the moment you are collapsing, you will end up generating your bits, and the other person will also generate their bits. So keys have been generated when you are collapsing at the end and not anywhere in between. So there is no scope for anybody to hack your information and look at it. So this is something which Einstein didn't want to believe, that entanglement or something like this happens. There might be something hidden or something which we don't understand. After that, people explored it more and more, and they are convinced. And I think 2 years back, Nobel Prize was also given for showing that experimentally what we call Bell's violation, or violation of Bell's inequality. So that shows that nature also provides this as a resource. So together, what we in a simple terms put is that there are three important resources which we are getting from nature, which has not been tapped and which is now being tapped for as a resource. Superposition, that allows to simultaneously explore all possible options. In a computing language, it's all possible solutions. There can be thousands of solutions, but you can actually explore. And interference allows us to engineer constructive interference towards a desired result and destructive to undesired results. What is desired results? Our solutions. There can be multiple solutions, but I want to have constructive interference towards my solution. Now again, entanglement allows us for instantaneous and secure information exchange. So these are the three key resources which has been exploited and controlled to build technology. In fact, it is also helping us to understand many things in nature. There are the way how chemical complexes are bonding together and how people can understand them better to build better drugs. So there is various other subsidiary questions which comes, but everything goes back to these three fundamental principles which we have understood from nature at subatomic level. So then there are I think this is what I mentioned. So when we had multiple number of qubits, we can write them all in all the superposition states. If I have n dimensions, I can write them and collapse. This is like, how do I mean, you're talking about atomic level, you might ask like, how is this going to help me to look at real-time computation problems? It can be a stock exchange problem, or it can be a traffic violation problem, or there's some famous problem called as traveling salesman problem, which means that a salesman enters a city and he wants to optimize so that he is not repeating going to any other places. He wants to go and visit every house and exit with the minimum resources. So this looks like not related to physics, and how can you model? The way it's all done is that I have this possible superpositions. Now 1, 2, 3, 4, 5, 6 is all possible routes you can have. Right? From A, you say go to house 1, house 3, house 8, house 10, house 20. Like there's some possibility. There is another route. Now you can actually treat them all as state 0, state 1, state 2, state 3, and then you can put in a lot of parameters, and then you can find out which is the optimal solution, and your wave packet should collapse when you make a measurement to one of your solutions, and you can say, oh, you can tell a salesman you take this route and that is minimum energy for you. I mean, I'm putting it in a very simple terms, but that is the way algorithms are targeted. That is the way it can be a stock exchange problems. When you say stock exchange, something is happening here, suddenly somewhere it collapses. These are all like correlations, right? I say entanglement is a correlation. Now, can we engineer entanglement in some way where we can put some modeling to way the stock exchange is working, and can we find out which is a better model to understand how stock exchange works? They're all hard problems, very hard problems. People are trying to see, can they target and solve them in next few years or something? But that gives, and now that is unrelated, not related to science or nature, but a similar way chemical complex, right? People want to discover drugs. How are drugs discovered? I mentioned about 50 atoms you have in superposition, and computers can't model them, right? That's what I said, because that's the supercomputer's capacity. Now, drugs, even coffee which we drink, has some 200 plus molecules composition, right? When you have so many of them, we can't model them explicitly. How are today's quantum chemists modeling it? They are breaking them down into sub-problems, solving them and putting them together, what we call parallelization. Now, what we understood from quantum mechanics is that there is superposition. The moment you are parallelizing, which means that you are making a measurement to all the subset, which means that you are losing some information when making a measurement, which means that we are doing a very a gross approximation of the solutions. So, if somebody is discovering a drug using such kind of chemical processes, then you are approximating a drug which can solve this problem. So, that is where the drug industry is trying to see a potential of quantum computers. You can get rid of such kind of approximation because you can take into account all the superposition which is happening and come up with a better chemical composition which can be a solution for certain diseases, right. So, that is because you have the possibility to keep all the superposition intact, the way the molecules, a large complex molecules happens, and then come up with your final output. So, this is how it is all scaling up from the way you are looking at. As I mentioned, 2 to the power of n dimensions, that is what 2 to the power of 50 would be 1 followed by 16 zeros or roughly, right. So, okay, I think I am also running out of time. I have further 5 minutes or something. Okay. So, let us see, I will quickly skip some things. I will try to directly take to, there are a lot of operations which we define for computation. If we just define some of those operations, we can do all of computation. I will just go for a measurements the way we understand them mathematically. So, when we have a superposition, your measurement always collapses to 1 or 2 of them. So, you can always keep repeating the measurement and you can get the same output, and that is how you find the solutions. So, the way we understand measurements is that you have 2 different states, it will be in superposition. This is the way it is always seen in quantum mechanics. Your measurement is collapsing it to 1 of them. So, if you repeat them, you can always reconstruct the superposition state. In some, we can repeat them in different bases, the way we do in a real life experiments. So, the general state, it is not just 1, right, if I just 0 and 1, but I can have many qubit states. I can always take sub states, 2 orthogonal states. It need not be just 0 or 1. For example, to give an example from light, it can be an H or horizontal vertical polarization, or it can be right or left circular polarization. They just have to be 2 opposite states. Then we can treat any of them as a qubit, and that is how generally it is done. That is what we call as a general measurement. So, we can also make a partial measurement here, because that is something which also becomes very important. When you start putting them in a mathematical framework, then we can start seeing how things can happen, right. So, what happens here is that if I take a 2 qubit system, I said I have 4 possibilities, right, 0, 0, 0, 1, 1, 0, 1, 1. In that 4 possibility, I just take one subset. Fourth one does not exist. The sum of these probabilities, like amplitudes are there. This is 1 by 4, 1 by 4, and this 1 by 2. It becomes 1. So, these are the 3 possible output. Now, instead of making a measurement on both, if I just make a measurement on 1 and not on the second, so which means here you can see the first qubit is 0, 0, 1. If I make a measurement, I will have 2 possibilities. First possibility, first qubit collapses to state 0. That is how here. First qubit collapses to state 0. Then the output of my second, then the output would be 0, 0 and 0, 1, because the first qubit has collapsed to 0. I have another option. What happens when we do experiment, or like when you look at first qubit can also collapse to state 1. Then I have an output of 1, 0. So, this is we call as partial measurement. If I have a 50 qubit or a 40 qubit, then I can make a wave packet collapse to the first few of them in particular state, and the rest can be in superposition. And similar, the way the measurements can be modeled is something like this, but you can treat them as solutions for some of your problems. So, partial measurements are something which kind of helps us to have informations of the subsystems in some particular configurations. So, this is a simple description of it. If I was having a single qubit, I would end up collapsing it either 0 or 1, but if I have a 2 qubit, I can still have a superposition of them, and then still one of the qubit is collapsed. So there is a superposition and collapse. Here there is no superposition, it is collapsing. So I can, that's how that's what I meant, like engineering. You can do operations and also engineering. You can make measurements and you engineer. So measurement plays a very important role in a quantum mechanical systems. Now we just go back before closing. I'd say now, if this is a superposition, I can use them also to generate random numbers, because every time I am making a measurement, I am collapsing. So I can take 0, 0, 0, 1, 1, 0, 1, 1, right? I can just give them some, or I can create a long sequence of them, and when you have certain patterns, then you label them as A, B, C, D, E, or whatever it is, your CAPTCHA code or your QR code, anything, whatever you want, you can generate from such kind of strings. So measurements are something which are, facilitating this such kind of dynamics in the system. So how your classical bits differ from quantum? So classical bits, we can measure them completely, and states don't change by measurement. Whatever is there, it's the same. In the classical bit, nothing changes. You can copy a classical bit, and you can also erase. Classical information can be erased, but in quantum, there are many things which are different from the classical, can be measured partially. You can't measure them completely, so you can be measured partially, which means if I have a 0 plus 1 superposition, my measurement will collapse it. I can't measure it completely. Your complete state is always secret, even to you. So even if I build a quantum random number generator, I can't have a control on where it collapses. The nature defines. That's what it means here. So it's decided by nature. You can't measure it completely. You can only make a partial measurement. Now state alters by measurement. When I say you have a superposition, if I'm making a measurement, the state has changed now. It is alters. Unlike the classical, there is no altering. And you can't copy a quantum state. There are theorems for that. I have not discussed them, but that's very important. It says you can't just copy any information, right? It helps you in security available. And you can't also erase quantum information. It remains there when it exists. Okay, so yeah. So I think this is a no cloning or no copying. As you say, if I have a state, in case if somebody says, can I copy a quantum information? If I say state 0 can be copied and state 1 can be copied, only then I can say that state 0 and 1 can. But what happens is, if 0 becomes 0, 0, if 1 becomes 1, 1, if I have a superposition and do this change, then it becomes 0, 0, 1, 1. It never becomes, a 2 copies of 0 plus 1. So that's what we mean. You can't copy them, right? If it is, it can be 1 by root 2 or it can be alpha and beta, any superposition, right? When we say that there is a linear transformation, which means that you can copy state 0 or state 1, but the moment you are saying 0 plus 1 and I do the similar transformation, 0 becomes 0, 0, then you will never be able to make 2 copies of the same. This is what we call one of the famous no cloning theorem, and no cloning of any arbitrary quantum state. So I will stop with this last slide. So what are the unique features of quantum mechanics? So initially said, okay, superposition, is it really exist? And all those questions came, interference, people started looking at entanglement. Einstein felt that it's not correct, and people came up with theories, and they all now agree that there is entanglement and you can measure them. Quantum systems are all defined by unitary transformations. They are not distinguishable. So these are all some of the features which we have learned from quantum mechanics, and we are trying to use them to build our future technology, including understanding nature to its best form, right? That's one of the most important things. So I'd like to close with one small statement why I'll take the questions. So what Feynman said when he invited people to work on quantum computing is that he didn't worry about, or he didn't talk about the security or all these aspects. But one simple thing which you said, by the time Feynman was giving this lecture around 1983, quantum theory was established, which means that nature's fundamental laws is quantum mechanics. Now, if you want to simulate and understand, then you need to do it the way nature is doing. Only then you can replicate something explicitly. So classical computers, whatever computers which we use today, are not based on principles of quantum mechanics, then we can't simulate nature to the best. So he said, inventing quantum computers, building quantum computers is inevitable. We should go ahead with it just to understand the nature the way it is done. That was his invitation for it, and probably for physicists like us, I think that's still the motivation. It's not that it's going to help solve various other problems. We just want to understand nature to the best. So if you have quantum computers, you can simulate. Why quantum computers and why? It's simple, right? If nuclear, something is happening at atomic level, or something is happening at a relativistic speed when the universe are being formed, the speed of light is so formed, and you can't, you can't simulate them in classical computers. But if you have a quantum computer, they are all quantum states. You can simulate them. That's as simple as that. So that's why the quantum technology in all aspects will be useful for various purposes. And I hope, yeah, okay. So thank you, and take some questions. Yes, I think I think yes, some we'll get a mic. Like I can't hear you, so I think it's getting the microphone.
Hello, you have told that it is not cloning and it is not precise about quantum mechanics and about the quantum technology part of application part of. Then how, when it comes to the part of the multidisciplinary application like your life science, your surgical devices, which we are looking at the present technology, life science where we are, then how this quantum technology will be helpful to us? Because that is what it's booming. Everyone are behind of quantum technology. So
no, see, that's what I said. There is a lot of things here when we're talking about life sciences, right?
we talk about AI applications also, no? Because that's how it's collaborating with quantum technology and
I
AI.
think I would keep these two. See, the way the market or people buzz, people who don't know the subjects a lot in detail sometimes float up with too many words. AI is a very matured advancement of a classical computing model, right? The quantum mechanics is a fundamentally different way of approach for the classical computers. Now, where people are using AI is to, you are trying to learn from the system and come up with a better algorithms or whatever it is. So people are trying, in a very ideal sense, people are trying to use quantum mechanics or quantum computers to improve AI algorithms, to make AI algorithms much more better or faster. These are the proposals. Now, your questions were multiple in a different way, right? But if I am saying about medical field, I was talking about how you can, look at the drug discovery things and how you are building sensors. People have built sensors, like I said, there are entanglement switch, right? I said entanglement. And now your lights, instead of using a laser lights, people can use entangled photons or very low intensity probes. So when you are trying to have any invasive method of detecting something in a biological sensor.
Because you have told that no, it's not cloning, because we are into the measurement part of it. So data part of it.
I'm still not getting your, when you say cloning, you can't clone a quantum state.
Copy it, right?
You can't copy or you can't
yes.
clone a quantum state. Yeah.
So how do we collect the data and develop the,
See, what I said here, I think there was I was talking about salesman problem or something like. Now you have a lot of data. Like all this data has to be modeled, right? Now your data can be a superposition of all these possibilities, and an optimal configuration of data is your solution. That is the way they are trying to, look at the data analysis of it. So data has to be mapped. Either it is a finance problem, or it is a biological problem, or it is any random huge set of data. So the problem again, when you have huge data, that's where they are talking about, right? What I said, you have 10 to the power 10 followed by configure possibilities. Now that is your set of data. So to store such kind of data, a quantum computers can help you, because, or like what is it, not storing, it says to process such kind of data, the superposition can help you. A smaller number of qubit can process large number of data. And now you have to map those data into the qubits language. So that's the way people are trying to map. Either it is biological modeling or something. But in the field of biological sciences, or like what people are trying to look at quantum, there are sensors which people are trying to look at. What happens when you are looking at any tissues today, the moment you are trying to intervene something there, you are altering a tissue. When you are altering, then you are not actually measuring how exact it is. But if you are using such kind of like what I am talking about photons here, photons are very low power. They are very unlikely to alter the structure of what you are trying to probe. So which means that you are getting it to highest. People have recently, in recent years, have shown that you can actually use quantum states to probe a very early transition of cell from a normal to a cancerous cells. because it may take a lot of time to mature and then detect in some way that there is some cancer cell detection, because the small threshold, the resolution in which you are seeing the transition can't be detected. But a quantum states can help you, because there are ways, you are not probing them with very high intensity and you are not doing any smudging. You can get a very good imagery. So these are the way people are trying to look at imaging. It's again lot of datas. When you have those datas, how you can map them into a quantum states and then extract them.
AI models are collapsing. There are some papers in Nature as well as they are coming in IEEE also. Then what is the solution? Because when you go for generalized way, GPT-3, from GPT-2 to GPT-3, they have proved mathematically that the model collapses because of generalization, and the heterogeneity will be lost. So we are getting the answers for two places which are 1,000 kilometers away as 100 meters.
Okay,
People
so
have, they are working on those things also by putting knowledge reasoning and so many other. The human interference is needed.
yeah, so I get your question, but I don't have any expertise in AI to answer your question. I think you should talk to people who are working on AI and machine learning.
No, this is best. Even with no cloning, number of states, let it be there, hundreds of states. If you are able to identify one state,
See, that's the way. In fact, when I was asked about, I see there's nothing against any other models, because that's the way we are building, and they are all like mathematically constructed models. And here we are trying to see how a physical way. Physics means it's not physics as our subject. Physics is the way the nature is defining, and that can be a better role. I think it's time to. It might take some more time for people to evolve and come up with proper answer for your questions. And
Thank you for the wonderful session, sir. I have a doubt. So in partial measurement, the fourth state does not exist, or
no, you just created such kind of state.
Using some gates will...
It is only to say that if I had created all the 4 basis states, in the other second measurement also I would have got a superposition state itself.
Okay.
Just to show that you can actually have a superposition, and you can also have a one state collapse with the partial measurement.
Okay.
We just engineered one state like that.
Sir, applying beam splitter twice in a particular fashion, it will bring back the earlier state.
It is flipped, right? 0 is becoming 1 completely. It's not just coming back.
Beam splitter twice.
Beam splitters twice here, it's actually not coming back to 0. You're beginning with 0, but you're actually getting back 1. I think, yeah.
So it is...
in this you are getting 0. I can actually change, I'm getting 0.
It is adding I also. So can you
because
please
you have high. So yeah, you can actually get back 0, or you can also get back 1, depending on the kind you
interference. Yeah. Thank you, sir.
It is very, see, why, and nobody would have cared if, at the end I said Feynman statement, right? No government would have come to fund quantum technology research if that was the reason. I said, like, why the governments don't care about science in general. I mean, they do care. I should not be very, they don't care so much like the way right now they are trying to look at investing on science research, is because if somebody builds, like many countries are trying to race to build the first quantum computers, because the moment you have a computational power which can hack into their systems. So it means that it's a threat to everything. It's a threat to national security, it's a threat to the commerce. Commerce is the least of it, right? They are worried about national security. In fact, people today, there's a, you can keep what we call, post-quantum cryptography has come in, thinking that people are building some models so that even if quantum computers comes, can they keep the information secure? And these are like still not a very solid basis, but people are building some such kind of security measures, right? So it is a very serious threat. It can be 5 years, 10 years down the line. Nobody knows, because we are all working on small scale quantum computers. But when it comes, definitely it's a threat.
Hello, sir.
Yeah.
Could you go to the slide on Mach Center interferometer?
Okay.
So in this, in the second beam splitter, is there something like a measurement has already been happened, so it collapsed to one of the eigenfunctions?
No. If the measurement had happened, then you would not have got an interference at all. See here, if you are seeing, when you say what measurement has happened is this, right? If I am making after the first beam splitter, oh sorry, you are selling after the second beam splitter.
No, because what it says is that before the beam splitter itself, there seems to be some collapse towards eigenstate.
Yeah, before the beam splitter, you are beginning with an eigenstate, that is 1, 0.
Yes.
I am beginning with an eigenstate.
Yes.
And then I am bringing it into superposition.
Superposed state, yeah.
Now on the same superposition state, I am again applying a beam splitter. And then I am not making a measurement. The output itself is this. If it has collapsed, then I would have got both the outputs. But every time, 100 times I measure, I don't get, like here, I am not having any probability. I am always getting everything here, which means that the output itself is a basis state, one of the eigenstates. I am not collapsing. Collapse is not happening here. It's because output itself is the state 0i.
So this means it has lost some kind of coherence in between?
No, it has not lost. It has had more, loss can also happen, but here it is systematically an interference. It is almost like you are controlling. The phase is coming here, but what is systematically happening is, it is going into superposition, constructive, and it's also destructive. Interference. Okay. You can have a constructive, say in a double slit experiment, we had 0 and 1, right?
Yes.
So now that's what you are capturing. One is constructive, other is destructive. Just capturing 2 of the interference pattern here. So there is a destructive there, constructive here.
So here you are representing the beam splitter using matrices. So in the similar way, don't we have to describe the mirror in terms of matrices? Because
mirror, what will mirror do? You are right.
Because 0, 1 becomes 1, 0 after the mirror.
Yeah, that's fine.
So
that's true. You are right.
Maybe that's what is.
That is not going to do anything. You can go back and do the math. You can put just a state change.
But this is something like collapsing a superposition. So
no, it's not collapsing. Mirror is only reflecting.
No. What the final result you get at D2, it's like collapsing to your eigenstate without doing a measurement.
Yeah, okay. When you say collapse, you are right. I mean, it's the way you are wording it. You are right. So, but it's when we say whether it was in superposition or not, it was not. Collapse, it is collapsing. It is naturally collapsing to the eigenstate. That's the way you are trying to say.
I expect to be one of like mod alpha square or mod beta square.
But alpha square is 0. I know, I'm not doing here. You are getting with this multiplication. What you are saying is that there should have been alpha or beta.
Yes.
If I had chosen some other configurations, not a 50-50 beam splitter, I can end up having. That's what I told. When I was talking, I was telling you, how do we engineer such that I'm not just getting this state, I will get alpha, beta. Then I can even begin with here itself. Instead of starting with 0, I can begin with alpha, beta here. If I begin with alpha, beta here, then also I will end up having a non-zero in both of them.
Okay.
Then measurement will collapse to one of them with certain probability. Then I will not have 50-50. That's what we call as engineering states and doing computation and other thing. But this is a simple going to the extreme of possibility here.
Okay.
It's a controlling interference so that I am demonstrating both one side is destructive and other side is constructive. But you're right, I can choose alpha beta, then I can end up having 60-40, 30-20, whatever configuration I want. But I can I can engineer them by doing this.
So this all revolves around the form of matrix 1i, i1.
Yes.
So I would like to understand why it is written in that way.
Okay, I'll say, so I had some slides I didn't say. When we are looking at any possible operations, we call universal quantum gates, universal set of quantum gates. It's not just this alone. You might have, in physics, people would have got exposure to Pauli operators, Dirac operators, right? Sigma x, sigma y, sigma z. What does that define? Rotations of the spins. Now, we need those 3 operations, and we need an Adamard which goes into superposition. And then we also need something called as phase gate, which has some slightly zero, some phase factor would come. They all should be unitary matrix.
Yes.
So if I have these 4 set of gates and then 1 2-qubit gates, what we call, how you can make 2 of them, 4x4 matrix, then you can do any kind of interpretations, combinations of them. I can use a combination of Pauli with this Adamard, and I can get any possible states I want. So we say if I have that set of few operators, I call them as universal set of gates. Using that, I can have any computation problem with a combination of those operators. We can do it just like in classical computers, we have NAND, OR gate or few gates, right?
Universal gates.
Universal set of gates. If you have them, you can do all computation. The same way we have set of gates. This is one of the basic set of gates. Or we can have a generic superposition state gates, and now that can be constructed by using combination of poly and Hadamard gate.
Okay, sir. Thanks.
Psi 2? For 0, 1, yeah, it will be 100%, yeah. Yeah, 0. Okay, so thank you.
Thank you very much, sir. Such a voluminous presentation on quantum mechanics and quantum technology. A big round of applause to Dr. C.M. Chandrasekhar, sir, for accepting our invitation and delivering this session. And also, we have Karnataka Science and Technology Academy has brought a policy paper on quantum technology, in which Dr. C.M. Chandrasekhar, sir, has also contributed under the chairmanship of Dr. Usha, madam, who is from BIT. The copy, soft copy available with us. You can visit our website and you can download that. And now we have with us Dr. M. Sai Baba, former director of the Resource Management Group, IGCAR, Kalpakam, and visiting professor at NIAS, Bengaluru. I would like to welcome him on the dais. Sir, please. So after this session only, we will be giving for a tea break. Sir, please. So before starting the session, I would like to give a brief introduction about Professor Sai Baba. He is an outstanding scientist and former director of the Resource Management Group at the IGCAR, Kalpakam. He was senior professor at Homi Bhabha National Institute, which is known as HBNI, and Dean of the Student Affairs and Coordinating Dean of HPNI at IGCAR. He has held the TV Raman Pai Chair Professor position at the NIAS, where he is currently visiting professor. He was with Ramaya University of Applied Sciences in Bangalore and served as registrar. He was the director of Center for Professional Development and Training in new initiative of the university. He was also professor at the University of School of Social Sciences, contributed to the fields of public policy and science communication. Professor Sai Baba is an accomplished researcher, scientific administrator, and institutional builder. He has made a significant contributions to implementing several high-impact activities relevant to the IGCAR and the DAE. He has contributed to diverse domains, including human resource development and access to scientific information resources, and financial management, workflow automation to move towards a paperless office, technology transfer, and intellectual property rights. One of his significant contributions was establishing the BARC Training School at IGCAR and steering its program until its superannuation. With this brief introduction, I welcome once again Dr. Sai Baba, sir, to deliver the session. Thank you.
Thank you. All zeros, okay? Yes. Yeah. Okay, so good afternoon to all of you. It's always good to hear about you, even though you yourself know about it, right? Sometimes it's good to hear from somebody says you're great. And then I remember once traveling in a train in Shatabdi going from Bangalore to Mysore. I was, I don't know, some of you traveled in the Shatabdi, there'll be a place where you'll face each other in the center. So there's one lady was sitting there and she asked my name and we got introduced. I thought we'll converse. Then she went into silent mode for 5 minutes. I thought maybe I was boring, I'm an elderly person, so what is interesting to talk to me? Then after 5 minutes, what she was doing in that 5 minutes is searching for my background, okay? So I don't have to tell anything about myself to her. Why I'm sharing this with you is that you have to be very careful when you talk about yourself, because the world has become so open that you don't have to tell about yourself. People will know about it if they want to know about it. Yeah, first of all, let me thank KSTA for inviting me here. It is all started. Let me also a priori tell you that I'm not like Chandrasekhar. I'm a non-specialist. I'm not a researcher in quantum science and technology, but understanding quantum science and technology. It all started because one of my domains of research is on science communication, which I do at NIAS. When I say science communication on advanced technologies. So for example, we did some very good work on AI. What people think about AI, not really developing AI algorithms, what you think about AI. So about in the month of December, Gujarat Council for Science and Technology was organizing a 2-day meeting on quantum science and technology, and they invited me. And they wanted me to be talking about the opportunities students have or researchers have, and how do they prepare themselves if you want to take advantage of quantum science and technology. And that's how I got into quantum science and technology, try to understand. So what I'm going to present in my talk will be to querying myself about what is quantum science and technology, why are we so much of excited, and where it is. I think today it is the next door, it will be there. So how many of you are physicists? So bulk of your physicists. How many are computer science people? Okay, so it's a physics and computer. Any chemist, any chemist here? Any mechanical engineering person is here? So some very minority, because you all believe quantum science and technology is physics, right? Physics and at best computer science, right? That's what it will be there. So 50-50 roughly. Some odd persons like engineering people also are there. Anyway, by education I'm a chemist, so I'm too much out of context. So let me, so this is where when I talk to KST people what I should be talking. So they said about physics and engineering of quantum science and technology. I moved physics to science because after all, and I'm going to tell about in my talk and tell why I want to say it's science of that part of it. Okay, so what happened? Yeah, see, very good that my talk is after Dr. Chandrasekhar's talk. He really talked so much. So it will be like a revision for you people. So don't ask questions from what Chandrasekhar taught you and then ask me to answer it. Okay, but he really introduced you about the quantum mechanics. And then, so what is actually quantum mechanics is essentially physics that deals with behavior of matter and energy at a very small scales, typically at an atoms level, and we are not talking about atoms, electrons, and maybe photons, or subatomic particles. That's what is the advantage of the quantum mechanics. And it introduced concepts that seem intuitively wrong. He was telling, two-slit experiment is going to only one place and not go. Intuitively, you think it is not correct, but that's what it is leading to, and that's what will have also give you an advantage to you, because it will do things which you do not think can be done. So that's where the quantum mechanics is all about, and it led to so many things like semiconductors, lasers. Laser is an excitement. I know laser is possible because of this understanding quantum states, and of course quantum computers. Everybody wants to think quantum computer. Anybody want to guess when quantum computers will be available? 5 years, 10 years, 1 year? What is the guess? 10 years. So it's very optimistically she's telling about 10 years. Good. So I think it is lead to quantum computers. Okay. But then I think, see, my job was made easy. He actually, Chandrasekhar introduced to you what led to evolution of quantum mechanics. The classical mechanics, all of your physics, many of your physics, you understand physics were there. The traditional physics could not explain certain phenomena, and then the quantum mechanics has come. One typical example is the photoelectric effect. So I'm sure he also showed the photoelectric effect, and it will be there. So I will save some time by saying photoelectric effect could not be explained by the conventional physics, whereas quantum could be done because electrons emit only light frequency exceeds a threshold. That's what it means. That means when you're hitting something, only when the threshold is crossing, that means that is introducing a new understanding about the material. So that's why the quantum has explained the photoelectric effect. Black body radiation, another thing which I think traditionally we could not explain. There is something called black body radiation is electromagnetic spectrum emitted by an ideal object absorbing all instant radiation. That's what the black body is all about. And why it is not, classical physics predicted radiation intensity would increase infinitely at short wavelengths, causing ultraviolet catastrophe. I'm sure a lot of you heard about this part of it, but it didn't happen. So the Planck solution is, it is energy is in discretized, you should be in the quantum thing, that you need to go to E is equal to h nu, and that is why it will explain, it will be there. And it led to foundations of quantum theory. I think he also showed about, it took 20 years, from photoelectric effect to the actual understanding. When the Heisenberg has given, it will be there. Simple thing like Compton scattering could not be explained, and then of course now it could be explained by the quantum. What is the nature of the light? Is it particle or wave? The dual nature, and that is what it led to the foundations of quantum technology. Quantum explanation is that Compton explained wavelength shift as an elastic collision between a photon and an electron. That means it is an elastic one. That is the reason why these things are happening. It will be there. Why classical physics has failed or could not explain certain things? Simply because classical physics assumes continuous energy, but quantum mechanics reveals energy exists in discrete quanta. This is something, it may look very simple today, but just imagine in 1900 when people thinking about it, it was difficult to conceive. And then the probabilistic nature, quantum mechanics is inherently probabilistic, describing system with wave functions and probabilities, unlike deterministic in the classical physics. So, particle wave duality, which I said. So, this much is about quantum mechanic principles. What are the quantum mechanic principles says? Superposition of and qubits. He's already explained to you what is superposition, interference and things like that. The new word which has come is called qubits. I will also tell a little bit after that. Quantum entanglement, we talked about entanglement. Now, quantum tunneling and control. That means whether you like it or not, there is always a possibility of some event happening. That is what we call as a quantum tunneling, and there is a tunneling microscope is available, which will all applied in material science extensively, because that takes care of, that makes use of the extreme low probability of tunneling happening, but that will help you to characterize the materials. So, this is where it led to quantum mechanics. Quantum mechanics is more than 100 years, 120 years. In fact, 2025 was the year of quantum science, and that is because 100 years old, and suddenly everybody now talks about quantum science and quantum technology. That is where, because it is an advanced application, you can do quantum computing, you can do quantum communication, you can do quantum sensing, so many things that can be done. And that is where the quantum technology is leading to, and there is always a technological impact of this. If it's only for doing some paperwork or publishing your papers, there will not be excitement, money will not be there. There is always a possibility of applying them, and those applications are creating a race to achieve success, and that is where the funding also will come, but there are a lot of challenges in realizing that part of it. Some of it I will tell. I think little bit about entanglement. I think something we need to understand. When I ask this question about entanglement, maybe you will not ask this question in a class, or in your teaching. If your student is asking, you will get angry. Okay, you can read, it will be there. So, entanglement means, the typical example is given is you toss a coin, either heads or tails, right? When it falls, it's heads or tails. That is 0 or 1. That is conventional computing. But when it is oscillating it, in which state it is? Is it in head or tail? And that is exactly what he showed, a sphere in which the possibilities are there. That means it is either in heads or in tail all the time. We do not know, as a function of time, if you see, it is there in all, and that is where simple entanglement, this is where the qubit concept has come and say, why you are doing only 0, 1, why not you do 0 and 1 also, and that is where newer opportunities have opened up, and that is where the entanglement. But then why is it, how do you realize it is the challenge now? The coin being tossed is nothing new, thinking that it is their heads and tails are nothing new, but the challenge is, how do you harvest this possibility of this coin being both in 0 or 1 as a function of time, and that is where the technological challenge is there. That is what is the entanglement, because I thought I will probably look into and see how do I explain entanglement to the people, if this is simply, this is what will be there. So, when particles interact in certain ways, their properties become entangled, and that entanglement is what you are making use of. He showed a nice picture of people claiming and then say it will be there. Okay. So, this is where entanglement is there. Oh, he does not want me to move. there's something wrong. Got stuck? Hmm? No, no, it's not moving. Even there, it's not moving. See? No, here also it's not moving. Yeah. Okay, and see, this is there's a lot. When you want to realize this entanglement and make use of it, there's a lot of system design and architecture. Coherence, he talked about, isolation, you can talk about, and all this will happen at a very low temperatures. I think that's where the cryogenics play a role, and you must have heard about dilution refrigerators, that means which will take down to micro degrees, less than 1 degree temperature. That means you need to maintain all these things at that temperatures, and hence cryogenic systems are there. You need to have controlled electronics and precisions, because when you transmit the signal, it will get lost because of the noise. Today, whatever quantum computing which people are claiming has a lot of noise. It really doesn't work till to realize its potential. So there's a lot of engineering is there. Stability is important when you're sending these signals. So, and people talk about quantum communication, right? We talked about, can we communicate without somebody breaking it or without getting into it? That's what we are talking about. Can it be secure communication is what we are talking about. The quantum key is generated and it is being communicated, and the global quantum networks, satellites can be used, or a fiber cable transmission can happen. But the challenge and the future impact is, there are a lot of engineering challenges, include the stability and miniaturization, how small you can make with potential to revolution security navigation. I think if somebody says, I have a method by which I can communicate very securely, you'll be very happy about it. I'm sure that all of you will see, if somebody, sometime back, when WhatsApp is being hacked, you move to Telegram. I know you said, I'm sure that all of us use WhatsApp free, but we want it to be secure. We don't pay 1 paisa for WhatsApp for using it, but we want it to be very secure. And somebody tells you WhatsApp is not secure, you move to Telegram. But you know what Telegram also happens to you. The idea is that it tempts you to so secure your information. So but there are a lot of challenges that are there. Now let me move to quantum communication. I think the quantum science and technology has multiple components. One is quantum communication, other is quantum computing, the third one is quantum sensing. That means, can we use sensing? I will probably briefly touch upon all these things in the coming slides. So what quantum communication does is, it will transmit signals by encoding information onto single photons and sending them through optical fibers or space, and detecting them with the quantum receivers. That means you need a sender and a receiver are there. It comes through either space or through a cable, and using classical channel for verification. It comes like that. But then it doesn't send the data. That's the biggest difference, is it doesn't send the data the classical communication way, but sends quantum states, usually single photons. That's what they will come. And it transmits information using photons. These photons carry quantum states, such as it could be polarization, phase, or time. This is where I think the photons are coming, and they carry the signal, and the receiver will decode that part of it. That means the fundamental difference is, it doesn't send data, it sends the photons or particles. Okay, this is something which normally, if you look at internet, you would always find this signal that you send from Alice to Bob through a key, and that key, what it makes you secure. And you have a receiver and yeah. So now photons travel through a medium. The photons then move through one of the following. What are the possibilities? One is through optical fiber, which already there, or free space links, that means from ground to ground, or satellite links. I can send through a satellite to a receiver. And you can see the quantum satellite communication makes it possible to achieve quantum links over thousands of kilometers. That means, and you can see China has already demonstrated a quantum communication, a satellite is already there. I think Chinese seem to be there everywhere. Anything you talk about it, they are there already. Though we don't like it, but we may have to accept it and say, yes, they seem to have demonstrated already. You must have heard about this Messier satellite, which is already demonstrated with quantum communication through using a satellite will be there. Now, where do India stand? That's something which we all have to think, where do we stand today? We have a national quantum mission. It's already demonstrated about 300-meter ground-to-ground transmission way back in 2021. That means from one building to the other building, it has been transmitted, and it could get back also. Just last year, I think we also demonstrated for about 1 kilometer. That means we are moving in the direction, but it's like a baby steps for us, where the Chinese already have a satellite, and we are just doing it. But then the researchers feel that I think in about 5 years' time, we'll be able to achieve what the quantum communication can happen. Now, I thought I'll just compare where the world is about quantum communication. I just tried, of course, China and the United States. Today, when we compare about advanced countries, somehow we have to bring China and compare. I just listed what are all the quantum satellites, free space, the quantum key distribution, city level networks, national backbone. What are all the things? I just listed certain parameters here. And then, and you can see where China is and where United States is there. And people believe or people agree that China is satellite-based quantum communication. It seems to China seems to be the leader. But when it comes to quantum computing and repeated technology means you know that there should be, when the signal is being transmitted, it gets lost, and you should have some nodes which will repeat it. And that's where the US seem to be good can be considered as a leader, with other people coming in, like be it Japan or Germany and things like that. They are there in between. And I just listed here where do we stand. Because obviously my interest is to know where do we stand. All of you also will be interested in seeing where do we stand here. Probably we can term ourselves as the first rising player focused on secure quantum communication. That's where all our research is focused upon. Now we move to quantum sensors. What is quantum sensor? It's a device that use quantum properties of atoms, photons or electrons to measure physical quantities with extreme precision far beyond classical sensors. That means I can measure it with very high sensitivity. Because you are using quantum states, they are very sensitive and they can detect small magnetic fields or weaker gravitational variations or tiny time differences, ultra small acceleration, because it can detect such small level, and the sensitivity comes because detect phenomena previously too small to measure, and work on GPS denied environments. Just imagine you're lost and then you don't have a GPS signal. That's where the military applications will come into the picture. It can be compact, rugged and portable. It's like a new generation sensors which what we are talking about. Now it's going to, if you can somehow realize these quantum sensors, it can revolutionize every field what we can talk about, starting from healthcare, where all of us will be interested, to mining, to energy, to whatever you can call will be there. But then I just want to emphasize, when I was preparing for this talk, it is not that you know the concept. To realize the concept, a lot of work has to be done by multiple fields that will be there. Just I listed here for atomic clocks, squid. Squid is already being used for medical applications, already there. You can see what are those materials we are talking about. Unless otherwise you develop expertise or establish expertise in handling these materials, the other things will be only a theoretical understanding about these quantum sensors will be there. You can see many things that are possible, but then I just want to list here that if you are a physicist and tell a theory, but somebody has to develop that material which will demonstrate or which can be demonstrated. So that means you a lot of material science, chemistry, engineering will be there. That's what my emphasis is always to tell you. The quantum science and technology is a combination of several things will be there. Just listed here what are those materials which are used in these quantum sensors. Many of them are already, these quids have been already used, being used for medical applications extensively. Though it's a very huge machine that is there for squid machines, but they are used for brain scanning or heart scanning and things like that. Some of them are already realized, some of them are in the process of realizing. Now, I want to move to communication. I'm sure all of you heard about this Moore's law, and this Moore's law in 1965, he told every 2 years, you all heard about transistors, microprocessors, and it was predicted that every 2 years it gets doubled. And it is a very empirical, and he told an empirical statement, and surprisingly, it sticks to it. The graph shows to you that, it seemed to be sticking to 1.95 is what is the, if you just go by this mathematical thing, it's 1. That means whatever he predicted empirically, he's still holding it. But then there are challenges which are coming, because today maybe it's not possible to do this far and far. It's like, you're on a travel, you have a suitcase, and you are going for 1 week, you put your dress. If you're going for 2 weeks, you have to put more dress. If you have to go for 1 month, what you can do? You have to take another suitcase. But airlines will not permit you more than that. What will you do? You should look for alternate. So what is happening is, today we are reaching a situation, it is possible that we may not be able to extend it beyond this part of it. I just, he's from Intel. I just showed here, where do we have this transistors all about. Oh, sorry. See, these transistors, microprocessors, really made a change to our lives. For example, personal computing, all of you hold laptops, or now probably a mobile phone which on your table, and then these are all enabled affordable PCs in 1980. I remember the first PC in this country came to our lab. It was so exciting at that time. It was 286. I don't know whether you heard about this 286. You have to put a big 3.5 inches, 5 inches of one floppy has to be put inside. During my tenure, it will become become small. Now you go and tell kids that they used to be computers operated by that, they will say, just laugh at you. But that means in our own lifetime, we have changed so much of change that is happening here. All this is because of these microprocessors becoming available now. Today, on your mobile phone, you are able to see, because you are able to compact them. And so you can see smartphones, AI, big data, healthcare and transport. See, while we are very happy using your mobile phones and laptops, but if it's not applicable for your healthcare, you will be worried about it. I think, the entertainment is only when you are healthy. So I think a lot of healthcare also is being utilized in healthcare monitoring, it will be there. But what are the challenges today? The challenges are, the physical boundaries seem to be reaching. Today we are in 2 to 3 nanometer nodes. That means just imagine these things are up 2 to 3 nanometers. But you know that when you use your phone for a long time, it gets heated up. You must have seen that. Normally, one of the fundamental limitation for any of these things is the thermodynamics of it. That means how much of heat that gets generated, that destroys your system, it will be there. So you will reach a level where probably we have reached there because of heat or power loss. And the more compact you want to make, more expensive it can be. So that means economic costs are there. Maybe we are reaching the end. That's what is the prediction. But normally what would happen is that every time you are challenged, humankind somehow finds solutions, it will be there. So if this is the case, what will happen to computing? That should be our worry, it will be there. So I think the physical limits which I mentioned to you, the cost, if you can make it very compact but it's expensive, then you don't want to have it there. And of course the heat and power, which I also explained, will be there. Now the question is, what will happen to computing? This question should come to our mind. What next it will be there? That's why they are moving to 3D chip making, 3D stacking. That means it's only making use of the space that is available. Maybe vertical integration to increase density without shrinking the transistors. But then maybe you can increase your algorithms instead of doing hardware. Many times if you are able to do things on hardware, a software, maybe it will give you much more benefit than the hardware it will be there. Of course, that's where quantum computing seems to be coming out and say maybe that is a solution for us. but there are also something called neuromorphic computing, that is brain-inspired computing is what people are thinking in terms of, or simply use photons instead of electrons. I think can we use this? So these are the possible future ways, but today we little bit dwell on quantum computing will be there. See, quantum computing, again we explain, instead of using 0 or 1, we are using 0 and 1. That means it will open up possibilities which are enormous, and those possibilities can be utilized. In fact, if you are able to realize about 50 to 100 qubits, you probably can do much more than what the current generation computer can do, what will be there. So we again, these things are realizable by superposition, entanglement, quantum interference, of course measurements. The thing is, these qubits, once they transmit, when they collapse, they also either become 0 or 1. I think you will be able to realize that part of it will be there. That's what will happen in the quantum computing. See this, I was listening to a talk organized by Springer people a few days back. The way he explained, as if the quantum computers are already available somewhere there. They seem to be available. I think, I just looked at the internet and said, yes, they are available from IBM, Amazon, or Microsoft. They are making available. All of you can access it by going there. But what they are giving is a physical qubits, not logical qubits. And they are only an experimental ground for you to learn how to use quantum computing. They are yet to be realized, because I think today, I think this is where what I say is they are available for us to explore what the quantum computing can do, but it is not real quantum computing. And if we just look at strengths, US has hardware scaling, private sector gains, cloud computing services. I think that's where US is concentrating. The China is on quantum communication, especially the satellite one, and EU, the European Union, is coordinated flagship program, sensing and materials, and Japan and Canada, specialized research, niche innovations. Of course, India, I just put it here and say, yes, National Quantum Mission is there. There is an emerging talent is what we are telling. All of you represent that emerging talent, which is there. I think this is where we are calling, we are rising contenders for these quantum world. And just look at big companies like IBM. What is good part of it, this development is, the giants have gotten, they are putting their money, be it IBM, be it Microsoft, be it all these people are putting their money, and of course some new companies which are developing exclusively for this quantum. That means earlier the funding used to come from government. Today the funding is coming from these giants. That means they see the possible advantages of realizing this, and hence the money is coming there. And I think IBM predicts that by 2029, they probably will have 200 logical qubits. Now just imagine 200 is what we are talking about, it will be there. That's what they hope they will be able to realize. Now, when you talk about all this excitement, we should not forget about what makes it happen. And that's where I listed certain materials which are important to realize these concepts or the possibilities. One is the superconducting materials. Superconductivity is known for some years now, that the superconducting materials, semiconductors and quantum dots. I'm sure all of you must have heard of these quantum dots. You would find in a big mesh a small portion which you call quantum dots, and you get excited, maybe a PRL paper will be there. But then that is where the quantum dots, the topological quantum materials, that means it can host quasi-particles, fault-tolerant quantum computing by resisting local disturbances. Essentially what we are trying to say is, can it be immune to the disturbance from the surrounding? Because you are always telling about sub-zero temperatures, right? That less than 1 degree, sub 0.1 degree temperatures, but any small disturbance can take away, that will be there. So photonic and two-dimensional materials. I think what I say to you is that unless otherwise the developments happen in this domain, you will not be able to realize the potential of the quantum computing. I just tried to list here materials used, what are the materials. The purpose of my talk is to somehow tell you it's important to realize the dream of quantum computing or quantum science and technology. It is only when you are able to realize these materials that were just listed here. I probably don't have to read. All of you must be hearing about these materials. I just listed here for on each of these things, which is the material. For example, in the quantum memory or detectors, you use some of these niobium nitride, or these are the things which you use there. Now, this is where I started my exploring quantum science and technology. Now, if you want to realize this quantum thing, where are the people? That's where I think the question to be asked, where are the people now? Now, the quantum workforce, I think tomorrow, I'm sure all of you are here, about 100 of you are here. Maybe all of you want to go and work in quantum computing. Good number, but 100 may not be sufficient, it will be there. The question is, where are the people? So, my focus was on to look at where are the people, or if you are interested in doing, for pursuing a career in this, what it is there. Well, I think the biggest bottleneck is not about building qubits, which I told you, which is itself by challenge. It is the training people, training enough people to develop software, integrate systems, and apply quantum solutions to real world problems. That's where we are looking at the people. That means there is a potential for developing this. Talent shortage is there everywhere. Not I think India is there. I think United States, everywhere you can see talent shortage is there. There are not enough trained professionals. And how that is being met? By national missions, university programs, or industry training. I think some sort of awareness, what we get out of this is something like in that direction. It requires interdisciplinary skills. There are very few experts in physics, computer science, engineering coming together. I think, we always say, I'm a physicist and you're a computer science person. We don't talk to each other, probably have a cup of tea or something like that together. This is the way the problem is coming. Is the cross-disciplinary courses are required, joint research is required, and there's a lot of software gap in terms of lack of robust quantum key distributors. You need to develop open source platforms. There's a global computations. Talent is concentrated currently in US and EU and China. I think we need to have people in other countries. India, Japan, and Canada. Just imagine even Canada and Japan are also, we are only building pipelines. India is there to look at it, will be there. So there's a lot of challenge in terms of identifying people who would work on this, and we also should have the talent. So nations are racing to build education pipelines, but will take years to balance supply and demand. Today, if you want, it cannot happen, right? So that's where awareness programs like this or discussions like this will help to see, yeah, well, I can contribute to here, I can pursue my career in this part of it will be there. If you want to pursue quantum science and technology, what should we have? The aspirant should have abstract thinking, just that imagine those 2-gate experiment which you told, 1 gate, 2 gate, and we will say why it's coming only here. You need to think like abstract thinking, programming, and a lot of experiments have to be done. Some of you should visit the science, there's a quantum, the cryogenic lab is there in IISc, and if you, I don't know, the part of the program, some visit also is there. You can see the type of difficulty that's required to maintain that laboratory there. You need to have resilience and adaptability. It's not that I get up and say tomorrow I have quantum computing on my hand. I think it's something like, it's a fast evolving technology. So what can we do? One is you need mathematical reasoning. If you want to work in the quantum science and technology, you have to have conceptualizing your physics concepts there, programming skills, experimental precision, interdisciplinary curiosity is something which we talk about, interdisciplinarity, multidisciplinarity, but very rarely we are there making use of that part of it. I just tried to list here, these are the things which are required, and this is what the courses probably you can take, and these are the career opportunities that are there. And I'm sure that depending on where you stand, I think you will be able to pursue it. Now, one of the biggest challenges in our country is specializing at very early age. I'm sure all of you are not students, probably you are already researchers or teachers. You remember we have electrical engineering, it became electronics engineering, then it became electronics and communication, electronic and telecommunication, electronic and blah, blah, blah. So many things are there. Then suddenly computer science came, we are happy about it. Now computer science, then moved to computer science and cybersecurity, computer science and AI. Now there are courses undergraduate level at AI. If you ask, go look at AI, can it be without computer science? But somehow students would like to do BTech in AI. That means we are the people, somehow in our country, we are fancy to specialize at very early stage. I will not be surprised if tomorrow one university will start BTech in quantum science and technology. I'm sure it may be there. Okay, there's a master's course in IISc Bangalore, a master's course on quantum science and technology. I would always say specialize in at master's level, it will be there. So why I say is, but then what is important is, you can always learn about it along with the other disciplines. We talked about materials, we talked about engineering, cryogenic engineering is there, we talked about structures, algorithms, but then at undergraduate level, you need to have courses, physics, computer science and math, but can also have some minor, major minor courses there. You pursue some quantum, just to know what it means, it will be there. You will gain some skills based on what course you have taken. If you are in PG, probably post-graduation is the time when you should specialize. When you specialize among all the things which are required for quantum technology, which is the one which you can do that. So maybe advanced quantum algorithms, hardware, maybe you can become a researcher, research scientist. If you are a PhD student, I don't know how many PhD students are there in the audience. If you are there, yes, some of them are there, good. So if you are a PhD student, it's a long journey, right? 4 or 5 years of journey. You would see, you will develop specialized expertise. It could be developing these quantum dots, or it could be developing those structures, or whatever it is, what we can be there. So, but then you can become this, and you can become a leading researcher or an academic faculty. Of course, the industry training is also very important. There should be industry, I'm sure there's a visit to one of the industries there scheduled in the program. Somebody from industry also come and talking about it. So you will apply your skills, including quantum programming, and you can become a developer or an engineer. So all of us have to play a role, be it academia, industry, government, and it is important to have interdisciplinary careers. That means we need to not have one career and then forget about it, it will be there. So each of us, the academia has a role to play, industry has to offer internships or corporate boot camps, find out where you are really. If you go to a cryogenic lab and see how difficult it is to maintain those sub-zero temperatures, you realize, you will say thank you to this part of it will be there. Only when you sit outside and say, I can realize it. So better to go and visit those facilities whenever the opportunity comes. Government has a big role to play. I'm sure that you must have seen today in the newspaper it has come, some 200 courses are coming on NPTEL for quantum science and technology. All of us, anybody who is interested should pursue that part of it. The industry also should play a role. So what I say to you is that if you want quality human resources, all of these things have to play a role, and you get an opportunity to say, okay, now I can pursue that part of it. Now, if you are a young researcher, many of you are, what are the steps I can take, which are the actionable? Sometimes you come to 3-day meetings like this, you are excited, you ask a lot of questions, and you go back with a lot of possibilities. Then go back and become busy with your routine things, what will happen, it will be there, and say you heard a very good talk. So there are actionable steps. I thought I can list actionable steps here. One is enrolled in specialized quantum courses. It could be online, or it could be some university offering, it can be there. Or seek industry, go and, somehow the internship doesn't mean that you have to spend months together there. Maybe 1 week, 15 days also will give you a feeling about what is happening there. Or apply for government funded fellowships. I'm sure government is coming with a lot of fellowship schemes which are there. Maybe you should take a break from what you're doing, get the fellowship and go and spend time in an institute there. You need to build interdisciplinary expertise. And of course, engage in global networks. I just listed down IBM, Amazon, many things are already offering. You can access their websites and make use of it for understanding this part of it. So you should be able to explore this part of it. I thought this is a very important step for me if India has to realize the dream of being there in this forefront will be there. Now, I heard somebody asking whether it will kill commerce, is somebody e-commerce it will kill, or it will happen something. So we seem to be having lot of apprehensions or People say, he said that no, we can do what a supercomputer cannot do within a minute. We all will get excited about that part of it. So what is very important for a technology to be realized is to take people along with you. That's where my research is on engagement with public. That's where I think you need to understand what are the challenges with engagement with public. If somebody was, the general public was asked to listen to Chandrasekhar, they will say, thank you, I don't want quantum computing. They will go back, because that is where we need to connect to the people and say. So what is important is you need to educate people, you need to have outreach, you need to have industry engagement. Industry people should come and tell what they are doing, what are the possibilities. The problem is the trust part of it. If somebody says, I developed, see, IBM said 2029, they will realize 200 qubits or 100 qubits. I mean, just imagine an IBM like Giant is telling that's possible. And the way the perception is that we will have tomorrow a solution for every problem, like healthcare, or somebody said about the e-commerce that it will kill. So this is where I think the trust and security concerns are important. There's always hype versus reality. We seem to be creating a lot of hype. Today, quantum computing can do wonderful. I can send my message, which cannot be interrupted by somebody, secure communication. But all those realizations would happen, not today, as somebody said 10 years or 5 years, a long way to go. But then a common man will think, tomorrow government gives you, government has already given 6,000 crores for quantum mission. Somebody can question, I don't have a road, why are you giving 6,000 crores to these researchers? So this is where we need to have hype versus reality. There's always a danger of exaggerating the possibilities. Then you get disappointed. The people will get disappointed, and the governments will slowly withdraw the funding if people oppose that part of it. So this is where public engagement is very important. All of you have a role to play. All of us have a role to play and say why quantum science and technology is so exciting. It will be there. So that, but then be careful about hype versus reality. Don't say that tomorrow it will happen. It is like a baby steps we are taking. You remember, some of you are married and have a small child. Then the child makes the first step. That's the very happiest occasion for you. You take nowadays pictures, post on social media. That happiness of that small child making the first step is so exciting. But today you go and tell the same child, I had excitement about walking, he will laugh at you. But then that is the excitement of the newer possibilities we are talking about. So we need to, I only put this slide to say, engagement with the public is important, not only about quantum science and technology, for all advanced technologies. Today, because people can be misled by the social media, right? The same social media can also say, no, don't do this, we are wasting money. So this is where the public engagement is very important, and that's where all of us have to play a role. Now, I just want to say there are challenges. What are the challenges? Quantum decoherence is, we said no, they come together, but they can go become decoherence. Scaling and control complexity. There are fabrication challenges are there, the cryogenic. Just imagine you want to maintain your cryogenic apparatus at 0.1 degree Kelvin. The type of challenge that has got is an enormous difficulty will be there. Of course, software and workforce challenges, which I told, it's not that even if I have all the money, there are no people. And even if you want to put all your time, you will not be ready because you may not have developed the skills that are required. It's not only writing the program, it is also realizing the materials that go into this part of it will be there. Well, quantum technology is not a replacement. Not that tomorrow my mobile phone will be replaced by quantum mobile phone, or my laptop will be replaced. No, that's not what it is. Quantum technology is not a replacement. Classical computing will remain dominant for doing everyday tasks. It's not that, don't think that your laptop is replaced by a quantum computing laboratories. And maybe most of us don't use the capabilities we have with us. Our phones, we use only 1% of the capability. But still we want expand i17, i8. Nowadays every year then phones will come, we go end up and spend money because it's more powerful without realizing that you don't even use 1% of that part of it will be there. So we don't need it. It is niche but powerful. Why we are excited is, it is powerful. It excels in optimization, cryptography and simulation. So that's where quantum computing is a challenge. But the struggles are error correction and scalability. Now we are talking about 200 qubits is what we are talking about. Though 200 qubits itself can be enormous, but then scalability can be a problem. Is a lot of interdisciplinary demand will be there. I'm sure how many of your physics people here? 50% of you. When did you study chemistry last time? Or when did you study material science? You want to make a material for physics studies? You will say some chemistry friend will do it. It's not our job, we will think. And especially computer science people say, that's all, don't tell me all those things, I will write my programming. So this is where the problem for all of us is, our thought process is, I'm good at this, hopefully good at this in codes, and I will continue to do that. We need to talk to people and realize what it requires. That's where the interdisciplinarity, multidisciplinarity will come into the picture. Very abused word, rarely happens in the reality. So that's where I think interdisciplinary demand, I told you, it's a physics thought should be there. There should be math, computer science. I put engineering also because if you want to realize those cables or if you don't realize those machines, you need to have a lot of these challenges there. And this is where traditional computer science is more software focused, right? You all agree that you write a program very efficiently. I agree that I'm not saying that it is important, but then it is much above that is what we are talking about, and that is where the quantum technology is there. This is my last slide. So I think quantum technology is not magic. It looks like, it's a magic, something will happen, very secure or very fast computing. I can detect new drugs. I can find solution to new health problems. All looks like a magic. It's not magic. It is carefully controlled physics combined with advanced engineering. That's what we're talking about. No magic in it. And what is very good about it is that India is growing research ecosystem shows that quantum technology is no longer limited to a few countries. Typically what would happen now, India is very proud of software, right? You just go and analyze and see which of it is our own development. We are more of a service provider. Somebody gives a car, you drive it. But somebody has to give a car to you. The good part of it is that today India is there when the development is happening. And that's a very extraordinary thing according to me. I'm very excited that, but we are there already. Government is thinking about it. India is not following, India is being there. That's where the quantum mission of India, 6,000 crores have given. You must have known 42 institutions, about 140, 150 researchers are working together among 42, 43 institutions, including IIScs, IITs. It is a very unique thing where all the people are coming together and trying to address this part of it. So this, and the good part is India is there. I think so we should be proud that we are there when things are happening. And if you are a student or a researcher, it represents a rare opportunity to help shape a technology while it is still being built. Just imagine you are already there. It's not that when somebody does, we also do it. But that's not the good. But then it is a rare opportunity of being there when it is being developed across the world globally. And that is where the rare opportunity for students and researchers. I see not many students sitting here, all of your researchers, I guess, or a PhD students. The quantum era will belong to those who understand both how nature works and how to engage it. It's not that, you remember when Newton detected the gravity, apple has fallen. We quote this often, but do you think that apple has fallen only at that time? It must have fallen number of years, number of times, and he also must be seeing that apple falling, but it has to be there to realize and correlate that part of it. So for me, it's a unique opportunity to be there, to understand the nature and contribute is what I think we will be there. And I stop here and I want to thank you for your attention. Maybe I want to end by saying that if you want to become a quantum science and technologist, don't concentrate on computer science, don't concentrate on physics. It's a combination of multiple things which are required. So you can say, sir, do you want me to study mathematics today? No, we don't have to study. But maybe you can collaborate with a person who is good at mathematics. Maybe you can come together and say, can we work together? So I'll stop here. And I think I always tell in my talks when I give a talk on a new topic, I don't know whether the audience is learning or not, but I learn. I understand, and that's where my attempt has been. I thank you for your attention.
Thank you very much, sir. Any questions? Quick one or two. So all are tired now. So on behalf of KST and on behalf of all the delegates present here, I would like to thank Dr. M. Sai Baba sir once again for accepting our invitation and delivering this session on physics and engineering foundations for quantum technology. A big round of applause to Sai Baba sir. Thank you very much. So now we have one more session. Sorry, just kidding. Now tomorrow we have at 10:30 session, and now there is a tea break in the canteen. You can join us. Okay. Tomorrow we'll meet. Thank you.
Can we take a picture together?
Yes, sir.
Outside or here?
Outside we can have a group photo. Before going for a tea break, I request all of you to join for a group photo. So it will be a attendance purpose. Bharata, ನೀವೇ ಹೋಗ್ಬೇಕು ಕ್ಯಾಮ್ರಾ